We will code and write this entire AI research paper that I just wrote just for this video to show you how to write and code entire AI research paper, and you can put your name onto this and it will be very easy for you to do something else, change this a little bit and do your own experiments and do your own real research. Step by step, everything explained in this course. This research paper is very beginner friendly to create. You don't need any tough mathematics, and it will be very easy for you to create your own experiments and do your own research on top of what I will teach right now. This GitHub repository is the repository for this research. It contains large language model that we will code from scratch and all of the experiments that we will do. And in this experiments folder, I have the base that I used for this research, and it will be very easy for you to add your own experiments. My goal is to create AI research lab, hopefully best in the world, and every paper we make, we're gonna make a full course on how we did it. Right now it's me and my Discord community, but I'm gonna be moving to different cities, meeting people and hiring people soon. And by making these videos, I can pay for the research, for salaries, for compute. And so just by watching this video, you are helping us advance science. Usually the most difficult thing in research is figuring out what to even do, what questions to answer. Answering questions is easier than figuring out what questions to answer. This is also the problem with large language models with humanities last exam, where large language models are tested if they can answer these questions. And if they can, they're gonna be good at doing research. But in reality, coming up with the questions themselves is even more difficult. And this skill of knowing what to work on is something you just build over years, and even most experienced researchers struggle with this. But by writing research papers, you will eventually become better and better at this. So when doing research, you will spend a lot of time thinking. It's like a reasoning and thinking. You will maybe be walking around the street, around the forest and thinking about your research. That's what a lot of people do. And you cannot rush research, publish it in a week. You need to spend a lot of time thinking about it. Of course, in this case, because this is a course and tutorial and we did a lot of thinking, then it will be a lot easier and faster for you. But if you are looking to create a groundbreaking research, which I actually have a goal for our company eventually to start doing research that's accepted to these conferences and everything, then we will spend a lot more time on each paper. Also decide what your goal for doing research is, and it's not gonna be to get hired at some company like OpenAI or DeepMind. If you get hired there are some benefits. But just spending every day, whole day, just because you want to get hired, there are easier ways to make money. And usually you will get a high salary after like 5-10 years of experience. And you can get a lot of money in other fields as well, even faster, where you develop a product or something. So your purpose of doing research needs to be different than making money or getting hired. Because it's the more difficult way to make money and get hired than other ways. And so your purpose can be to contribute to science long term or to answer things, find answers to questions you are curious about. And also, there is no some hidden mentor that once you meet them, they're gonna discover your potential. I highly doubt, and Robert Greene talks about this, so it's all about you sitting down and figuring out your own life. Maybe it's good to have friends from AI research field, talk to them, get their opinions, see what everybody else is doing. But at the end of the day, it will be you sitting down in your room and figuring out what you want to research and do. Also, you can do what I do. So you can either make YouTube videos or publish blog posts, LinkedIn posts, and either create your own company or some AI research lab or join. It's also very good to join OpenAI, DeepMind, but you need to understand like why you are joining it, why you are joining. But anyways, whatever your goal is, I do recommend you do your research in public, publish, make these either videos or blogs or posts on social media. So for me, I want to keep improving these research papers and courses. I want to publish everything, make courses so everybody can learn, and this will accelerate science. And I plan to keep improving our research papers. As I said, eventually we want to publish in conferences and hire people and create a proper lab. But it took me a couple of years to figure out what exactly I want. So you will also take some time to figure out what you want to do and why you want to do research. So then let's start with the course. You can join my school community to become AI researcher. We have exclusive courses here and community that are not available on YouTube. It helps me fund my research and make better videos as well. So everything from math, PyTorch, neural networks, attention, LLMs, and more courses. Click the link below and watch this video to learn more what this school contains. So I'm gonna assume you have some basics on doing AI research and large language models or machine learning or PyTorch. So if you don't have any basics, I recommend watching this video, Become AI Researcher from Scratch full course. I'm gonna link it below in the description. And then it's also good to watch this Coding Llama 4 from scratch. So if you want, you can watch this because this is also very beginner large language models, because in this paper, in this course, I'm gonna assume you know about large language models, a little bit at least, and or checking out this Code DeepSeek v3 from scratch. You don't need to watch the entire thing, maybe just a little bit to familiarize yourself. All of the links below the video. Go to your GitHub and let's create a new repository. I will name it Noptims for novel optimizers or new optimizers. You can name it whatever you want. So all of the code and my paper will be here. I'm gonna add description, development of new neural network optimizers. I'm gonna make it public. I recommend you share your research and everything publicly, otherwise this is gonna make it so much better. So people can learn about you, know about you, you can build your network. Keeping it private is not gonna work well for you, because you will do research that nobody knows about. Same philosophy goes back to my channel. I'm sure a lot of people have watched my videos and this will help me a lot build a network. So I recommend keeping all of your research in public. And then I'm gonna add readme, so I don't need to add it manually later. I'm gonna go git ignore and select Python and license MIT. This is the most permissive license, and create repository. This is the repository we created. I'm gonna copy its URL. So I'm gonna clone the repository locally to my computer. I'm using Google Anti-Gravity right now. So I can click here and then paste the URL, and then I'm gonna select where to clone it. After you clone it, it will offer you to open this new repository in a new window or the same window, so you can open it just like I opened it here. If you don't know how to clone from GitHub, then you can watch some Git and GitHub basics introduction on YouTube, so you learn about GitHub and what cloning is. Or you can ask ChatGPT or AI to help you. So you need to be able to set up your environment like this. This is basic like Python introduction, or setting up Python environment and opening it in a code editor. So you can watch YouTube videos or ask ChatGPT if you don't know how to do this. But anyways, once we open this, we're gonna start creating some new folders here. Let's create a new folder, models. And inside new file, layers.py for Python. Then next to that file, I'm gonna say new file, components.py, and a new file, moe_llm.py. So this is where our large language model will reside. It's like mixture of experts LLM, or you can name it whatever you want. Now let's open components.py. Let's open and let's start writing some code. So I'm gonna import torch. I'm gonna import torch.nn as nn, torch.nn functional as f, and from typing import tuple and optional. Now you may type this all out, you may copy these imports if you want from my code, but I recommend you type manually all of the code here. We're gonna write now, so you understand how it works and how it's written, etc. First, we will code a single expert. So let's create a class expert which inherits from nn module. And I'm just gonna add comment single expert network, essentially a feed forward layer. So single expert is just a feed forward layer. So I believe you understand how experts work, how mixture of experts work. If you don't, I listed videos and courses you should watch to understand how large language model works, but I can also just tell you. So each of the feed forward layer in neural network, it looks like this. So you have expert 1, 2, 3. So each of them is just a feed forward classic neural network, multi-layer perceptron. And then we have router to select the expert based on the token that is being generated right now. Then I'm gonna initialize the expert. So we just pass in self and dimension of the model. So dimension of the feed forward. So imagine this as having the first input layer. This neural network has first input layer and then expands to this hidden layer. So this is the D model. This is the input, the token. This is the size of the token that this expert gets. This is the token embedding. And then it expands to this middle layer, which is gonna be processing this token. So this middle layer is usually 4 times bigger than this token embedding input size. And then we contract back. So it's like input, hidden, and then going back to the token size. And this is 4 times bigger. So this hidden layer of neurons contains a lot of the facts and knowledge and rules for processing the token. Like if you are talking about some sports, this hidden layer would contain like knowledge about rules of the sport, famous players in that sport, etc. So I'm gonna have, this is the token size, the first and the last, and then the feed forward is the middle, the 4 times bigger usually. Okay, and then dropout, this is good to prevent overfitting. And we're gonna initialize this super, oh my god, this super is just initializing this NN module. And then this is the first linear layer, so our input layer. So as I said, this goes from the D model, which is token size, to the hidden layer, which is 4 times bigger. So that's our first linear layer. And I'm gonna show you on the image. It looks similar like this. Just imagine that this middle layer would have 8 neurons instead of 3, because I said that whatever the input token, this gets a token, this is 4 times bigger, and then we go back to token size. And so this contains a lot of like knowledge about whatever so each expert is gonna be specific for something. The neural network, the large language model will learn for each expert to assign some specific knowledge. Like this expert is for math, this is for sports, this is for history, etc. So I explained all of this in the courses, and you can watch on YouTube more courses about mixture of experts. So then, second linear layer will go from the hidden back to the token size, and we don't need bias for these. And the dropout, we will initialize dropout so we prevent overfitting. Now some people don't use dropout, but I use it. It worked better with my experiments. And then let's define forward method. So the forward method will be how we use. So here we just initialized this network expert, and forward is where we use it. So first, it's gonna look like this. So I'm just gonna type all of this so you can see. So, it's gonna start from here. So this is the input. It gets passed through the first linear layer. And after we pass through the first linear layer, so it's going like this, and then it's gonna be passed through activation function, SILU in this case. And so imagine now we are at this point. We have values for the middle layer, for the hidden layer. Dropout means we will ignore some of the activations, make them 0, some of the neurons make them 0 in the middle layer. And then we're gonna multiply this middle layer with the weights to get the output of the token size. So this linear will multiply the hidden layer with the weights to condense it back to the token size. So that's how we process. This is the classic feed forward. So this is just one expert. Then let's make sure we save all of this commit to GitHub. So you have connected your GitHub. So I'm just gonna press generate, and it's gonna generate some message and sync. So you can learn more about GitHub in other YouTube tutorials if you don't know about it. So guys, I switched to cursor because I just couldn't disable the auto completion AI generated suggestions in my editor. So let's continue with cursor. Let's now create a top K router. So router will choose which expert, one or multiple, to choose based on the current token. So just create a class that inherits from NN module, and router that selects top K experts for each token. So top K most relevant, I should say, experts. First, I'm gonna initialize the top K router. So I'm gonna say dimension of the model, which is the token embedding size, number of experts, and how many of those experts we should choose. Default is 2. And then I'm just gonna super init to initialize the parent class. And so I'm just gonna assign these values to the local variables, top K and number of experts. Then we will define gate, which is just a linear layer that goes from the token embedding to number of experts. So it will just look at the token and convert this to some numbers, and we will use those numbers to assign probability or likeliness or affinity for each expert. So how much it wants to choose each expert in particular. And we have this noise. There are some issues when choosing an expert. The neural network can learn to always choose same experts. And then those experts learn, and then they're good. And then when it even tries to choose different experts, they didn't learn, so it gets punished. So then it gets stuck choosing only few experts, but it's suboptimal, because if it instead balances out choosing all of the experts, then in the end it will perform better and be able to save more data into like each expert and knowledge and development of the experts. Now let's define forward for the top K router. So we're gonna start with the forward itself. So X is our tensor that contains all of the tokens. So it can be a three-dimensional tensor, so each token, but all of the tokens are in a sequence. So sequence length or context window or conversation is just a single conversation with all of the tokens in that conversation. So that's sequence length. And then batch size. So you can have multiple conversations. All conversations are independent. So usually you would have these three dimensions: tokens for token embedding, and then multiple of those tokens in an array. That's sequence of tokens for that conversation, and then multiple conversations that are independent. And this will return tuple, which is torch tensor, torch tensor, torch tensor. Gemini gave good explanation of the three things this router will return. So let's start here. Top K indices is the second thing. So it's just index of the selected experts. So let's say expert 2 and expert 5 are selected, because we are selecting 2 by default. And each of the expert will have some weight or importance of how much it contributes to the final token. So maybe this will have 70% weight and this will have 30% weight. And you will understand this better later. So those weights are multiplied. And so those are the weights for the top K experts. And router probabilities will return all of the probabilities across all of the experts. This is necessary for the auxiliary loss later. So these two just return for the top selected experts, and this is probabilities for all of the experts, but we will learn more about later. Then I will just add some comments. So the input X which is the input tensor with batch size, sequence length, D model, you need to be able to understand what this means, like these dimensions, like intuitively. So I explained that well in my AI research from scratch course. And then what it returns: router weights, expert indices, router probabilities. And first thing we want to do is take the X input tensor and then get its shape into these three variables. So dimension of the model and sequence length and batch size. Get shape of these three separately. So the size, how many conversations, how many tokens in sequence, and how many dimensions per token. And this is going to be maximum number of tokens possible. So maximum sequence length. Then we want to compute router logit. So now we want the router to select experts. So I'm going to say router logits equals to, and don't worry, these words will become brighter blue color later when we start using them. So we will just pass X through our gate, which we defined. Oh, we didn't define it? Okay, never mind. We'll define it later. Oh, we did define it here. This is the gate, so it's a linear layer that goes from D model to number of experts. But we can easily pass X, even though X has this big shape, it will just, so these ones will be copied. And it will just go from D model to number of experts instead. And so it will return batch size, sequence length, number of experts. So that's gonna be our logits. So it's like logits are showing the affinity, like the bigger number, the bigger affinity for this expert, so that expert will be selected. And we're gonna add some noise during training only for exploration. So as I said, we will randomize a little bit the logits so it doesn't get stuck reinforcing same few experts every time. And so if it's training and if we have some noise that we want to add, if it's more than 0, then we will say noise is equal to, we will create the noise. So those will be random numbers of the shape router logits. So we have some random value for each of the logits, yeah. And we will multiply with the standard deviation here, 0.1. And so router logits will be equal to router logits plus noise. It will add noise to all of the logits. Get full probability distribution for load balancing loss. So we need this later. We also need to get this. This is the third thing we return. So router probabilities, we will do softmax over all of the logits. How softmax works is if you have some logits numbers like 1, 5, 6, 7, it will put all of those numbers between 0 and 1 and make all of them add up to 1. So it will squish them between 0 and 1 and make them all add up to 1 so that you can look at that as probabilities now. And along last dimension, so along number of experts dimension. So for each token, we just take its experts and just do over experts just for each token separately. And select top K experts. This is the first and the second thing we return from this gate. So there is this torch.top K function, and we just pass in the logits, and that's going to be assigned to top K. And because router logits has this big shape, we just want to select over the last dimension, so for each token. So that's the last dimension. Sorry, my bad. This top K means we are selecting top 2 experts. So 2 out of whatever it is number of experts, which could be, for example, 8. And so we say top k weights, just like we calculated with the softmax, these probabilities, we will also use the same thing to calculate weights, which will also add up to 1. So as I said, weights, we will multiply output of each expert with certain weight for that expert. So weight will say how important this expert was. So if we have 2 selected experts, one gets 70%, the other gets 30%, then this one will have 70% influence when multiplied, and this one 30. So the same thing. And we will return all 3 things that I mentioned. So it's also a bit difficult to explain for me, but don't worry, I'm gonna repeat all of this as we code following things. You will understand, because it all goes back on itself and you will understand it. So the top K router will choose for each token, it will choose, for example, 2 experts out of 8 possible experts or whatever we have, and it will return the indices of those experts, for example, second and fifth, and weights of those experts, for example, 70% weight, 30%. That's based on the logits. Basically, that's based on how the neural network classifies importance, which numbers it gives here. And weights will add up to 100%. And then router probabilities for all of the experts for that token, which we need later to make sure it's balanced when it selects experts. It doesn't just select only 2 experts all the time, same 2 experts. Next class will be a lot simpler, I believe. So it's just mixture of experts class, also inherits from NN module. So we will combine our router and experts here. So let's first initialize self, dimension of the model, which is the token embedding size, dimension of the feed forward hidden layers, which is 4 times larger usually than the model size, although it's not always. Number of experts 8 as default. We are selecting 2 experts out of 8 for each token. Dropout 0.1, 10%. Load balancing weight. We'll talk about this later. The goal here is to make sure that the router doesn't always select same experts. So we want to make it select different experts. So initialize super. And then I'm just going to, all of these variables, I'm going to assign them. Okay, these 3. And create experts. So experts will be module list. And just call this expert class. Pass in dModel, DFF, and dropout. So for every expert, so number of experts is 8. So this will create 8 experts in this module list. And then we will create router. And that's it, I think. Yeah, that's it. So that's all we need. So for top K router that we defined here, we just pass in number of experts, dModel, and top K number. Then let's define the forward method for mixture of experts. So how does the data go through this class? So input is xTorch tensor, and output is tuple, which is torch tensor and optional torch tensor. Let's see what this is. So first, input is our classic batch size, sequence length. So this is just our list of conversations. And returns output, which is gonna be processed list of conversations. So it's gonna be the same list of conversations, but it will be processed. So what does mixture of experts do? Mixture of experts, it comes after the attention mechanism. So I'm just repeating now the structure of LLM. And for each token, it will just modify it a little bit, process it based on maybe context around other tokens. You know that in attention mechanism, information from all of the tokens will be blended, added into every token. But attention will only look at the previous tokens for every token. So for every token, it will just add information from previous tokens. But now that information is just added with a plus with plus sign. So just adding a bit of this vector to this vector. And so feed-forward networks or mixture of experts will take this just added vector that has these numbers that are just added and process them somehow, refine them, inject more information into them. So imagine this as like processing. So attention is adding information and feed forward is for processing information, adding more data, analyzing it. The output is same size as the input, same shape. So every token just gets processed. So there is no next token generation here. So this is not generating next token. That's only the last output head at the end. So this is just for processing information. Maybe for understanding for the LLM what each token means and how it relates to other tokens and injecting new knowledge and analysis, etc. And then we have this auxiliary loss. This is just a number that neural network, that the LLM wants to make as low as possible. So this number will show how imbalanced expert selection is. So to put it simply, using this, we are trying to make the large language model choose every expert equal number of times. So we don't want it to choose some expert more frequently. We want each expert to get equal number of tokens in general on average. And so if some experts are getting more tokens on average than others, then this auxiliary loss will be higher number. And so the loss, the error, will be higher number. And this loss will be later added to the general large language model loss. So it's trying to minimize the general loss. And so it's trying to minimize this one as well, because this is going to be added. So in short, in summary, auxiliary loss is trying to make the LLM to give equal number of tokens to each expert. In this example, you can see that our mixture of experts layer will return this auxiliary loss besides the output, the process tokens that I just explained. And this auxiliary loss will be added to total loss at the end. So that's the total loss. And then we do backpropagation with the total loss. So we want to minimize this total loss, total error. So again, we're just going to get the shape to these variables. And we will pass X, our input, through the router to get our expert selection, router probabilities, and all of this that I described about the router. And initialize output tensor. So this is the output that we will get after processing. And it's all going to be zeros, and the shape will be same as X. Let's explain next piece of code. With Gemini, it's easier. Just listen to the theory, and then we will code it after, and then I'm going to repeat it, explain again shortly as well. So we are looping through experts. So for each expert, we're going to go one by one, and for each expert, we will process the tokens that expert got. In our code, I'm going to say process each expert as a comment, and for expert index in range, so in range all of the experts, I'm going to say find tokens routed to this expert. And this is how we will do it. Expert mask is equal to expert indices equal to expert index, and also dot any along dimension, last dimension. So remember, what does this mean? So remember, the first iteration, we are gathering all of the tokens from the first expert and then processing all of the tokens for the first expert. So remember that each token has two experts assigned. So here we are checking if this current token that we are processing, if this first expert is at any of the two places. So the first selected expert, the second selected expert. So is this current expert within those two experts that are selected for the current token? And so this expert mask will be the same shape. So it will be batch size and sequence length. So basically for every token in our context window, in our input, it will have true if that token needs to be processed by this current expert, and false if it doesn't need to be processed. That's what this expert mask will have. So you can see here that previously we got, for every token, we have two experts, two indices. So then for this particular expert in the for loop, we are checking in that list of tokens where each token has two experts, if this current expert that we are checking is contained within that list. So we will check for all of the tokens at once. Now this may be a bit confusing, but maybe if you understand it, rewatch this or ask AI to help you, then eventually you will understand it. So expert mask is batch size sequence length. So for each token it has true or false. This token does need to be processed by this expert, or this token doesn't need to be processed. So then if expert mask.any, which just checks if any of the values in this expert mask is true. So if this expert needs to process even a single token, so even if its single token has true, then we will process. So get tokens for this expert. Expert input is equal to x and expert mask. This part will be easiest to show on an example. Let's say we have our x, which is, for example, this is the first token, second token. So we have list of tokens, which is that conversation, second conversation. And then for expert 0, let's say first token is sent to expert 0. And then this one is not, this one is no, no, and yes. So each of the tokens has its own true or false. And the shape of this expert mask will be 2, 3. So 3 tokens and 2 conversations, each having 3 tokens. So it's gonna be like this. First token, second token, first token, etc. Sorry, third token. And I will show you this example in the Python code. So this is what I just explained. And this is our mask. True, false, true, and false, false, true for the second conversation. And if we apply this mask to the x, let's just see what we get. So we get the first token, third token, and sixth token. So first, third, and sixth have true. So it's like, it's now just one sequence of tokens. It's flattened the batch and sequence dimension into a single dimension. Now it's just a sequence of tokens that had this true. So if x, the full size of the input, is 100 tokens, if only 10 tokens are selected, expert input will be a smaller tensor of size 10. Then in the code we will add this. Expert output will be self.experts and choose this particular expert. So expert is just a list of experts, it's module. And choose this particular expert and pass in expert input, which is a list of these tokens for this particular expert. That will pass these selected tokens through our expert, which is a feed-forward network, which is linear, relu, linear. We defined this in the beginning of the video. But in reality, we are using silu, not relu. Silu is more complex and it's better function. You would use relu only for some other simple things. For example, in DeepSeek, sparse attention, and some other things. And remember, we just need to pass in a single token when we are processing that token. That token is not looking at the previous tokens. That was happening in the attention mechanism. So in this feed forward network, we don't need to pass the token and then look at all of the previous tokens. So that was actually at first confusing to me as well, but I just realized that was in the attention mechanism. And here we just pass the token itself and process the token itself, the vector, and nothing else for that particular token through this expert. Then maybe a bit trickier part. So I said each token is passed through 2 experts. And for each of those experts, we need to multiply the output with some weight and the output here and then add. So if the first expert for that token has weight 0.8, we will multiply the output of that expert for that token with 0.8 and add that to 0.2 times the output of the second expert for that token. And when we add those weighted outputs, then that's our final process token. To understand next piece of code, let's look at this scenario. So of course, we are selecting top 2 experts as always. And let's say we are currently processing expert 5. So all of the tokens for this expert 5. And so let's say this current token has experts 2 and 5. And let's say weight is 90% for expert 2 and 10% for expert 5. That's the data we already have. So here we need to grab this 0.1 or 10% and multiply the expert 5's output. We must not accidentally grab 0.9 and multiply expert 5's output. So expert 5 is 0.1 here. First line of code we will add is mask for expert is equal to, and then we check if expert indices is equal to expert index. So looking at this line of code, we will check. So if expert indices is 2 and 5, expert index is 5, then this will yield false for this one and 5 equals 5 true. So the mask for expert will be false true like this. So that's gonna be a sign for this particular token. Now I'm just gonna show how to add this in the code. So we are here. I'm just gonna say mask for expert is equal to this line of code that I just explained. And so let's see the next line of code. Positions is equal to mask for expert, and then inside expert mask. Let's see what this does. So remember, 2 experts are chosen for this token, and each of the experts has its weight, so 0.9, 0.1. And so we have false true because we are currently processing expert 5. So now we need to turn this false true into 0 and 1 for indices. So we will use this 0 and 1. We will use 1 to select this second weight, 0.1. So you see here, this is weight at index 0, this is weight at index 1. And so this is going to be false and this is going to be true. So we need to convert this false true that we have into just an index, saying that from this we want to pick this one that has index 1. So this may get a bit of confusing. So looking at this line of code again, positions is equal to mask for experts, and then index this with expert mask. So let's first remind ourselves what these two are. So this expert mask is for this particular expert that we are processing, so expert 5, showing true for every token it needs to process and false for every token it doesn't need to process. You can read it here as well. And then mask for expert, remember, if we have token 0 has experts 2 and 5, then it will be false true. And false false if it's not contained, and 5 3, so it's true false for expert 5. So mask for expert is actually for this particular token, if it's using this particular expert or not. And expert mask is for this particular expert, showing which tokens in the sequence it's using. Now check this out, this is interesting. Both of these arrays, so this array and this array, is showing you a list of tokens. So first token, if it's using this expert or not, second token, if it's using this expert or not, third. And here as well, first token, if it's using this expert or not, second and third. And so what we will do is this second token is not using this expert. So we will just remove this completely. That's one way to do it. You could also remove if both of them are false here, but it's maybe faster, easier in this way to use this array to remove tokens here that are not being used. So this line in our code will remove those tokens, and then we will only be left with tokens that are being used or processed by this expert. It's also explained here what I just described. If you want, you can read, but at the end, in this example, instead of having 3 tokens, we will just have 2 tokens at the end, because the middle token is not processed by this current expert 5 from the example. We will see later how we use these positions, so it will also be easier for you to understand. Now we have .float and .argmax last dimension. So let me continue with this example to explain this float and argmax. So now we have this filtered tensor, filtered list of just these 2 tokens that are using this expert 5. So it's second selected in this token and it's first selected in this token. So when we say .float, it will convert true false into 1 or 0. So false becomes 0, true becomes 1. So now we have this instead. And because we converted it to numbers, we can now use .argmax, and -1 means along this last dimension. So we will compare this 0 and this 1. This is the last, most inner dimension. Which one is bigger? Argmax, which one is bigger? This one is bigger. And index of this is 1. So the result of argmax of this token will be 1, because it's going to look at the index of the biggest number. And result of argmax of this row will be 0. It's just the index of the biggest number here. You can read through this, I explained this right now. And so positions will be 1 and 0. So for the first token, the weight for this particular expert is at index 1. And for the second token, the weight of this expert 5 is at index 0. So we will pick those weights to multiply later the output of the expert 5. Next, gather weights only for relevant tokens. So again, let me just do all of this. And we also have .squeeze. So let's explain this part of code. I'm gonna continue with the same example. Token 0 and token 2 are processed with expert 5. And these are the weights. And so, as I said, the index here is 1, index here is 0. This is what we calculated previously. So we had, token 1 is not processed, so it's filtered out. So the positions that we just calculated is 1, 0. This is the vector 1, 0. So index 1, index 0. And router weights, the full tensor weights for all tokens. So in the first step, filtered weights. So we will just grab weights for only the tokens that we are processing with this expert, using this expert mask. If you remember, expert mask is just showing which tokens are being processed for this expert. So it will be token 0 and token 2. So if these are router weights, we will ignore this token. It's not being processed, because token 0 and token 2 are being processed. And so when we apply this router weights and then expert mask, we will just get this. So array of, and this is contains, this is for token 0 and token 2. Now this is 2 by 2 matrix or tensor. But if you look at indices up, it's just 2. So it's just one array of 2 values. So we wanna pick this guy and this guy. And we can do that using this gather. But to use this gather, we need to match their shapes. So if this is 2 by 2, we will also make this 2 by 2 by putting each of these into its own array. So that's why we will just unsqueeze. If I scroll down, we will unsqueeze the last dimension, which means it's gonna look like this now. Each of them will be in its own array. And now we can use gather to pick the index 1. So whatever is at index 1 here and whatever is at index 0 here. So if I scroll down to show you, dot gather -1 and then indices. Indices is actually just our positions. So position 1 and position 0. And so that's how we select. And -1 means along the last dimension or innermost dimension. So we process this one, pick index 1, we process this one. So this is the innermost dimension. So I recommend you play around with this. You need to maybe get some feeling for like these dimensions if you don't have strong basics. You can also check that in my AI from scratch course, AI research from scratch. Or you can ask ChatGPT to give you more examples, to give you some tasks that you can run in Google Colab or in Python in your environment, to get the feeling for squeezing, unsqueezing, indexing, and all this good stuff. At the end, we get this 2 by 1 matrix. Did I earlier say that the indices were 2 by 2? I meant 2 by 1. So it's gonna be 2 by 1 matrix. And so this is the weight for the first token, that we multiply the expert of the output of the expert 5 with this weight, and for the second token the output of expert 5 for multiply with this weight. And finally we get this dot squeeze, the last dimension. So this will remove the innermost dimension. So our current tensor is like this, but we want to remove this innermost dimension. So we just get this array of these numbers. And now the shape is 2. So it was 2 by 1, 2, 1, but we removed with this with squeeze last dimension. So now it's just 2. And you see what it looks like when you squeeze this innermost dimension, the last dimension. And then what we want to do, so as I showed you earlier, we already have this output tensor. We are collecting, when we are processing each expert individually, we are just adding outputs to this tensor. So this output tensor is same, it's defined before experts here. So now we are processing experts and we are just adding output of each expert to this. So output, but for only for tokens that are being processed by this expert. Let's ignore this unsqueeze for now. So we have expert weights, which is just our array of weights. So for each token, so for each of the tokens, to multiply the expert output with this weight. So I explained this. I don't want to repeat too much. Maybe it's boring for some people. You may also ask ChatGPT to explain this again if you want. And we will need this unsqueeze so we can multiply properly. And then add the result to existing output. We are accumulating every expert's output in this total output. And so this will work well because weights for one expert, for this particular token, weights from one expert will be added, the weighted output, and the weighted output of the other expert will be added for this particular token that we are currently processing. So at the end, we will just have this token. As I said, weighted output of the one expert plus weighted output of the other expert gets added, and that's our token. And by the way, if this is not 100% clear, don't worry. Like if you are beginning with this, see this only a couple times, it will be difficult. For people who've been doing this for a few years, they might, it will be easy for them to understand. But don't get discouraged like others understand it, I don't understand it, which it's expected if you are don't have too much experience. So that's it for the experts. Now let's do the auxiliary loss. The goal of this again is to make sure that every expert gets equal amount of tokens. If some experts are getting more tokens, then the loss will be higher, and neural network will learn to minimize loss, so it will learn to divide tokens equally among experts. So let's just define the beginning value. If it's training, then we will just say auxiliary loss is equal to self.compute load balancing loss, and we will define this later. We don't have this function yet. And we will give router probabilities and expert indices. I will explain. Let's just see that we return output and auxiliary loss. We return from this forward method of the mixture of experts. So we return the output, the tokens, process tokens, and the auxiliary loss. Remember that router probabilities are for each token, the probabilities for every expert for that token. So it's gonna be batch size, sequence length, number of experts. So all of the experts for every token in the sequence. So it can be like these probabilities for this particular token, let's say. And we will use this in our auxiliary loss to calculate, to make sure that every expert is getting equal amount of tokens. Also, this is useful for back propagation because we are sending the probability distribution, so PyTorch can adjust the weights to select better probability distribution. It answers how strongly did the router prefer expert X on average. And we don't want it to prefer any expert, we want it to be equal for each expert. And again, let's remind ourselves, expert indices, a tensor containing the integer IDs of the top k experts that were actually selected for each token. So for each token it says 2 and 5, meaning that each token, like this token, got expert 2 and 5 selected. And so the loss is simple actual usage, which we get from our indices that I just explained, times average confidence, which we get from probabilities, which is the first thing that I explained. So router probabilities. But don't worry, we will understand all of this better. Let's see how it's coded. So in our code, let's actually define this function that we just used. So compute load balancing loss. And it's gonna initialize with self, and then router probabilities that we mentioned, and expert indices. We'll see later how these are used, so you will understand them better. And we will return torch.tensor, which will actually be just a single number, the loss. And let me add this comment. Compute auxiliary loss to ensure balanced expert usage. This encourages the router to distribute tokens evenly across experts. Then let's first code and then see on an example what it does. So compute the fraction of tokens routed to each expert. f.1 hot, so we are one hot encoding, and we're passing in expert indices, and number of classes will be number of experts, and converting this to float. Let's see what this does. This is example. Let's say for this particular token, expert 1 and 3 are selected. The output of this line after we process will be these two one hot encoded vectors. So let's say we are out of 4 experts, we are selecting 2. So this means that expert 0 is not selected, expert 1 is selected, and 0 and 0, these are not selected. So that's the first selected expert for this particular token we are processing. And the second selected expert is at index 3. So for every token we are generating these two one hot encoded vectors to show which out of the maximum number of experts are selected for this particular token. So this line will convert this shape, which was batch size, sequence length, and top k, which is 2, into batch size, sequence length, top k, and then number of experts. So each of these top k will now have a vector of size number of experts. It will be one hot encoded vector. I'm gonna summarize. I think it's very easy. So imagine this expert indices is just an array of 2 numbers, so 1, 5. And then instead of having 1, 5, we will have like one hot encoded, so 0, 1, 0, 0, 0, 0, 0, 0, 0. So there is 8 experts. And for the 5, we will have 0, 0, 0, 0, 1, 0, 0, 0. So that vector. So that's gonna be expert mask. It's gonna be like this, but since we are selecting out of 8 expert, this will be of length 8, not 4. And then we will just convert all of these integers into floating point numbers using .float, because later in the code we will need to use this in a fraction. So Python needs this to be in a float number. And we will use these one hot encoded vectors to count how many times each expert has been used. So tokens per expert is equal to expert mask.sum. So now we are summing these one hot encoded vectors along this dim 0, 1, 2, which I will explain, but we also have divided by expert mask.sum. Let's understand it with an example. Let's say we have just one batch, which means just one conversation. And that conversation has 2 tokens, and each token picks 2 experts. So we know that. And so let's say there is total 3 possible experts. So out of 3, each of the 2 tokens gets 2 experts. And so total slots is 4, which is 2 tokens, each having 2 experts. And let's see what these slots are. Let's say token 0 gets experts 0 and 1, and token 1 gets experts 1 and 2. So the expert mask is the one hot encoded vectors that we just generated. So we have one batch, which is one conversation, one sequence. That sequence has 2 tokens. Each of the 2 tokens has 2 experts selected for that token. And then each of the experts is encoded with one hot encoded vector that we just did. This is what it looks like. So for first token, we're gonna have expert 0, which is just gonna be encoded like this. So this is the first token, will have this and this, expert 0 and expert 1. And second token will have expert 1 and expert 2. Then dot sum and dimension 0, 1, 2, we sum across the batch, sequence length, and top k, top experts too. So what will this do is this will just sum it up like this. So it will just sum how many times expert 0 appears. So just sum all of these numbers for expert 0, sum all of the numbers for expert 1, sum all of the numbers for expert 2. I know it's a bit confusing, so actually it says here we are summing across these first 3 dimensions. But when I look at how we are summing, it looks like we are summing like the number of experts itself. So it looks kind of weird and confusing. But you just need to develop intuition by looking at this couple of times, thinking about it. So at the end, after this sum, we will collapse all of the information about token, position, everything. We will just have how many times each expert was selected. So expert 0 selected 1 time, and then this and this. So this is the resulting vector, 1 to 1. So that's going to result from this sum, which is, again, kind of weird. We specified these 3 dimensions that we're going to collapse, and then it looks like we are actually summing across this last. But we are not. You just need to get intuition, because summing across the last dimension would mean we sum 1 plus 0 plus 0. So that would mean that we sum across the last dimension. But this means we are actually summing across this, like the second to last. All of these. And that sum is this first part. And then we are dividing by this expert mask dot sum. Here we're just gonna take this array, which was 1 to 1, and then divide by the total amount of tokens. So you see, our goal is to convert this 1 to 1 into something that's gonna add up to 1. So we get like probabilities or percentages, I should say. So 25, 50, 25. So the first token selected 25% of the time, second token 50% of the time, and 25. So that's our goal, to get this. So the way we will get that is we're gonna divide this count for every expert. Each of them we will divide with the total amount of these counts or these experts. So there is 4 of them in total. You see, 1, 2, 3, 4. That's how we get them to add up to 1, so we can look at them as percentages. And our load balancing loss or auxiliary loss will try to push these weights of the gate so that this vector is actually 0.33, 0.3, so it's equal for every expert. Let's see the next line of code. Compute the average probability of routing to each expert. So router probability mean, it's going to be router probabilities, which we already passed. We're going to remind ourselves. So we do the mean across 0 and 1. Remember that router probabilities is the output of the softmax before we pick the top k. So it's raw probability distribution for across all 8 experts for each token. So each token's how likely it is across all 8 experts for every expert. And it's gonna sum up to 1 per that token. And mean across batch and sequence length will say on average how strong was the router's desire to send tokens to expert X. Let's see example. So let's say we have a batch or sequence of 2 tokens and we have 3 experts. And so for first token, these are the logits, or I should say probabilities, not logits, probabilities. and for second token, these are probabilities. So we average these columns vertically. So that's what the mean does across batch and sequence. So 0.1, 0.1, the average is 0.1. On this spot, the average is 0.6. And on this last spot, the average is 0.3. So the result, router probabilities mean, it's going to be this vector. So for each expert, first expert has this average probability, second this one, and third this one. So that's our router probability mean. Comparing this to our tokens per expert, which we calculated earlier. So tokens per expert has this top k, so we cannot backpropagate through it, it's not differentiable. But the PyTorch can backpropagate through this router probabilities when we take all of the probabilities. So when router changes weights slightly, the logits or the probabilities that are created from those logits for every expert might change from 0.8 to 0.81. So this is differentiable. Check out my course on AI Researcher from scratch to learn more about derivatives and gradients and this stuff. But when you are just selecting indices, if you change weights slightly, the index of the expert will still remain 5. The index will not go to 0.0015. So that's why it's not differentiable. Because you just selected this expert. There is no this smooth transition between experts, the continuous transition. So not smooth, I mean continuous. And if the weights change enough, then it will snap from expert with index 5 to expert at index 6 or 1 or whatever. But this snapping is what's not differentiable. There is no continuous function between them. So in our loss formula, the first part has no gradients where we select indices, and the second part that shows this probability distribution, it is differentiable, I should say. So Gemini is explaining it in detail, so I will also explain it in details. So non-differentiable and differentiable means that here, when it's differentiable, neural network or PyTorch will know and calculate how to change the weights so the probabilities get more for this expert, for example. It will be able to calculate using the chain rule from mathematics, from calculus. But it will not be able to use chain rule for this variable because it's not differentiable. It's not a continuous function. Check out my course, as I mentioned. So why do we need both? Why do we need probability distribution over all experts for every token, and which experts were chosen, their indices, to calculate this loss? Because the router can cheat if you only look at probabilities. Let's say we have 100 tokens and 2 experts, and the router gives to every single token, it gives 51% for expert A and 49% to expert B. Now let's say we are just choosing one of these. Here probabilities look very balanced. So this would have a low loss. But the problem is we are choosing top one, highest probability always. So this would choose expert A always and never expert B. So if we just use probabilities to calculate loss, it would seem like this is good, but it's not actually good. So we also need to include this selection into calculating loss. Main thing to note is we are not picking based on these probabilities. We're not picking 51% expert A and 49% to pick expert B. We are just picking the highest probability one, so top one, every time. Let's see our formula, how it applies to our example. So we have usage, the F to be 100%, which is 1, and probability for that to be 0.51. So the loss is 0.51, very high here. plus 0 times this probability, which is just 0. So the final loss is 0.51. Now let's expand our example to understand this better. So let's look at 3 scenarios to see how the math actually plays out. But let's first code that. So auxiliary loss is torch.sum tokens per expert times router probability mean, which I just explained, times self.number of experts. And we'll see on the example why. And then this will just return auxiliary loss. So this is it. Times load balancing weight. So this is just how important this loss, how much we want the neural network to focus on this, so we can make it bigger or smaller. So if this is bigger, it will make the loss bigger. So usually this number is small. So we don't put too much effort into this load balancing loss. The main effort is going to be on the main next token prediction loss. But let's just see some math examples to see what happens in different situations here. Let's say we have 2 experts, and so let's check our formula. The first example I already explained, so we looked at this example. Now we would multiply this sum by 2 because we have 2 experts, and that's done to normalize the loss value, because if you didn't multiply by the number of experts, the more experts you have, the smaller your loss would be, just because you have more experts. Not because your models is improving, but just because you have more experts. So let's further investigate why we multiply with the number of experts. So in a perfectly balanced system, every expert gets exactly 1 over n, 1 over number of experts traffic, because traffic is divided equally. So fraction, the number of tokens this expert gets is 1 over n, and probability of this expert being selected is also 1 over n, because each expert should have equal probability and equal amount of tokens. By that logic, we can see that in this example, the loss will be proportional to 1 over n squared. So the number of experts, as it grows, the loss shrinks quadratically. And this is not real example, because here you wouldn't have number 1, you will have some number of tokens or some other number. Or this number 1 would be influenced here by this f. But anyways, what we just need to understand that as the number of experts grows, this loss will actually shrink exponentially, or I should say quadratically. So we need to multiply it with the number of experts. So it's 1 over n, the scaling. So in our case, where the expert A gets 51% and it always gets selected, we add that to expert B that never gets selected, the sum is 0.51, and we multiply by 2, and that's our final loss. 2 is number of experts, which I just explained why we multiply to keep this normalized. Scenario 2, we got 90% probability for expert A. Let's say this is average probability, and 10% for B, and so this A always gets selected. So now the loss is even higher, because not only does it always get selected, but its probability is always high as well. You see how this multiplication, what multiplication does is, if both of them are high, then the product will be very high. But let's see this perfectly balanced. So probability is 50% for both, and they get selected 50% of the time. So it's 0.25 times 2. Here, sum times 2 is 1. So that's the perfect loss. It is a bit weird that the perfect loss is not 0. So like 0, it's like 0 error, 0 loss. But this is how it works for now. And DeepSeek GRPO is trying to replace this, and other methods to trying to replace this auxiliary loss. So the neural network doesn't need to learn two things, like the main loss and this auxiliary loss. Okay, congratulations, we finally wrote this file components.py. I recommend you commit this to GitHub, do that occasionally. And I think other files should be faster and easier to write, to understand. Let's go to layers. Here we will define attention mechanism and transformer block. So I'm gonna import torch, NN, functional, and also this torch tune.modules. From this import rotary positional embeddings. So this needs to be installed. So let's create new file, requirements.txt. And here we will just write libraries we need to install for this. So datasets, this is from Hugging Face, transformers, torch tune, which is the one that I just mentioned, and torch AO, we will see this later, and matplotlib for graphs. So we will use datasets to load data and tokenizer. Transformers, are we even using that in this one? I'm not sure. So you will need to set this up with virtual environment and then pip install. So you can just check this video. My AI research setup, code locally, run on Google Colab or GPU Cloud, SSH, GitHub. Check this video. This includes how to install and set this all up. Link in the description. So rotary positional embeddings is invented by Sujian Lin. I always mention him on my channel, so he has a blog post and X account you can follow if you're interested to read about science, about research. He works at Moonshot AI. He's invented this after 11 years of blogging, so you cannot do it overnight. It took him 11 years, and this is used by everybody. So in 10 years, people can become very good, successful researchers. So I'm also from components, import mixture of experts, which we just coded. So we're importing what we just coded. And now let's create rotary positional embeddings. So initialize dimension of the model. This is the token dimension. Now I'm calling this token dimension in what we just coded in components, so I should have same name maybe. So it's just the token embedding size or model dimension, and then maximum sequence length, and initialize the super. And so we're gonna initialize this. So passing the dimension of the model, maximum sequence length, and this is the base for calculating rope. So I have these two videos, rotary positional embeddings and rotation matrices, and this rope as well. So you can watch both of them. So maybe this one is more important, and I'm gonna leave both in the description to understand rope. You can also watch rope in other YouTube videos. This is a bit complex. It will take you a few times to understand, but you don't need to master it right now. You can watch if you want, or you can leave it for later, because the way we will code it is very simple. So let me just show you here. Okay, so we will just pass our input through the rope, and that's it. And we will not code this from scratch. Now you could code it from scratch. The reason I'm not coding is because this is very fast implementation. It trains the model faster. But these videos that I showed you and other videos will show you how to code it from scratch. Sorry, I forgot to say the main purpose of rope is to tell you when you have a sequence of tokens, the order of tokens. So dog is chasing a cat, or cat is chasing a dog. It's very important which word is where. It indicates who's chasing who. So you do that with rope. If you don't use rope, I had a bug where my rope was not applied. Then the model did not get any information which word is at which position. So it just had a bunch of words it needed to figure out, so it struggled. And it does that by rotating pairs of dimensions of the token. So you have a token vector embedding. These two dimensions, it takes like this pair, next pair, next pair, next pair, and rotating them with a rotation matrix. So I'm getting into math here. So looking at a vector, so these two dimensions, these two numbers, looking at this, it looks it as a vector and multiplies with a rotation matrix to rotate it. But you can understand this in the courses that I explained in more detail. And by how much it rotates the dimensions, that's how it encodes, that's how the model knows which token is where, by how much it's rotated, like tokens relative to each other. But this rope has a specific requirement for the shape. So it should be batch size. What's T, bro? I forgot what's T. Sequence length. T is for like time, I guess. So sequence length, number of heads, head dimension. We'll talk more about this in the attention mechanism, like what is number of heads and head dimension and this stuff. So let's go to multi-head attention, initialize, dimension of the model, which is just the token embedding size, and then number of heads, max sequence length, max context window, and drop out 10% here. So you know this is the architecture of the transformer, and whenever like these lines mean like the token is going through the transformer, and this token has some size, it's a vector of some size, and that's the model dimension. So the token, the size of the token is the model dimension. That's like the main thing for the model, the main dimension. So I have good tutorials for attention mechanism, which I think I mentioned in the beginning of the video. So coding Llama 4 from scratch, coding DeepSeek V3 from scratch, coding Qwen 3 from scratch, and AI research course from scratch. So you can check those and check other attention mechanism videos. It's explained too many times on YouTube, so I will not explain it now. All of the links below the video. So I will assume you know what query key value vectors are. So when I say heads, what I mean is query vector and key and value, all of them are divided into equally sized chunks, heads, and each head is calculating it separately. So first head of the query key value are interacting, second head of the query key value are interacting, third head is interacting, and I'll just summarize how this attention works later, but this will be more like a summary, not like full explanation. Okay, so let's go into init. Model dimension. Okay, I'm just gonna save these variables into these local variables. So dk, I think this is the dimension of the key. We'll see. Yeah, divided by number of heads. As I said, we're gonna make query key and value same size as the model or the token vector. It doesn't have to be same size. Actually, a lot of the times it's smaller. But in a small model, small large language model, then it can be same size. And so let's create this query key value, and it's gonna be a linear layer. And let me quickly explain what query key value is. So each token has query key and value. And query, and when token is looking at previous tokens, it has its query. And you will multiply query with every key of the previous token. So query is like, what information am I looking for? So the goal of the attention mechanism is to get some information from previous tokens into this token. It's like enriching it with context. So what information and how are we going to get some information from previous tokens into this current token vector, current token embedding? So each token will have query. It's like, what am I looking for? And then each token will also have key. Key is like description of what information it contains. So when you multiply query of this token with key of this previous token, it's a dot product. So you can check what dot products are. So if the number is small, then there is not too much affinity. It means like these tokens are not so relevant to each other, or it's not important to take information from this token to this token. It's not so important. If the dot product between this query and some other key is high, it means this token is very relevant for this token, and then later we will take a lot of information. So how do we take this information? So we use value for that. Now the difference, so every token also has value. And the difference between key and value is key is describing what the token has, what information it holds, what information it will give you. And the value is the actual information it gives you. So there is a difference. Description of what it is and the actual, like the thing. The thing and the description of the thing are different things, separate things. So to summarize, so query is what am I looking for? Key is what I contain, description of the thing I contain. And the value is what I will give you, the actual thing that I contain. So for this token, when I'm trying to blend all of the information from previous tokens, I will actually add every single value vector. Just add. But I will multiply every single value vector to this value vector. So remember, I'm not adding value vector to the token directly. I'm adding a value vector to its value vector. I'm just adding value vectors. So I will add every single value vector just with plus. That's how you combine information from two different vectors with just plus. If you have this vector, like presenting some information, if you combine them with a plus, it will add that information. It works in neural networks. I don't know if it works in like other things, math and stuff, but in neural networks, that's how you can add information, combine. So anyways, I'm gonna add every value to the current token that I'm processing, every previous value, but that value will be multiplied with that single number, which is dot product between query and key, that says how important this value is. So if the dot product is a small number, close to 0, then this value will be multiplied with 0, or not with a number very close to 0. So when you add, it will just add a bit of like small numbers, so it will not change too much this value. But if the dot product is higher, then you will basically add more information. The information will not be so diminished. And you will add more information from this, because value is the information. So that was kind of summary. So then at the end, every token has this value that's enriched with values of all of the previous tokens, not the future tokens. We don't want it to look at future tokens because we are trying to make it predict the future tokens. It doesn't know. So just looking at the previous tokens. And so now this value contains information about itself, what the token actually is, and the previous context. Like there is a tree, fish, wind, it's blowing hard. So, and then this token is maybe a flag or a ship that's moving. And so it takes context that the wind is blowing and stuff. And so here I'm just generating these query key value vectors. But here is the trick. You don't need to generate it 3 separate times. You can combine it into a single calculation. So within your GPU, within your graphics card, you don't need to send information back and forward, which is slow. Sending information is actually slower than computing it, than calculating. most of the time. So we just gonna calculate this all at once without going back and forth, send separately query key value. So going from the D model to D model times 3. It's times 3 because we will do all 3 of these quick query value. And as I mentioned, now key query value, each of them will be same size as the token, but it doesn't have to be. In huge LLMs, I'm pretty sure the key query value is a lot smaller, 5 times or 10 times smaller vector than the huge token vector. But in small models like this, we can make it same size. And we don't need bias, although I've heard some people using bias also. But this is more common without bias, I believe. And we also need this output, so it's similar. So output is gonna convert the value back to the token. So remember, at the end of attention mechanism, we added all the values. But now for every token, we need to convert this value that's enriched with other tokens, by the way. We need to convert it back to the token itself. So that's what this output will do, going from the value to the token itself. And that's at the end. And I will also define rotary. And by the way, I'm not processing anything in these lines of code. I'm just defining it right now. So later we will have forward pass to process this and you'll see how it works. So then define rotary, which is our class that we made here. So I just need to pass in this dimension of each head. Now this is a bit weird. So we have model dimension, which is actually gonna be same dimension as key query value. And we are dividing by number of heads to get dimension of each head. And what heads are is you basically, instead of calculating whole query times key and adding value, you separate it into independent heads, independent parts. So now this head of key, the first head of key, is just interacting with the first head of query is multiplying with the first head of this key, of this token, and then adding the first head of the value. So each head is separate. So heads can learn different things. So I guess this dk is the dimension of the head, which is a bit confusingly named here. Maybe it should be like head dimension or head dim or something. But it is what it is for right now. Okay. So let's go next. Dropout. Oh yeah, that's just pass. This is the rate of the dropout probability. And let's now define the forward pass. So this is our input, which is batch times sequence length times token embedding. Just all of the tokens and conversations and everything. And so we need these shapes. So the first shape, a number, will be batch size. The second will be sequence length. Here I think I had a mistake, so I commented this should be deleted instead. So anyways, I'm gonna pass now input through query key value linear layer and then generate query key value. So now let me see what this is. So as you can see, this will be a single tensor that's 3 times larger than the model. And now I want to separate it into 3 tensors, which will be equally sized, query key value. So I'm going to do that here. So this is maybe a bit confusing. So we already know that X is shape batch size, sequence length, and then we have token dimension, token embedding. But because we pass this x through this linear layer, the last dimension will be 3 times token embedding dimension, like this. And then we will split this into something here. Let's see what we split this large vector that contains key query value concatenated into these things. So first keep in mind that the first 2 dimensions remain the same. So number of different conversations and order and tokens in each conversation remain the same. But now we do something with this key query value long vector. First we split it into 3. We will have key query and value. We just split like that, so easy. Key query and value split into 3 equally. And then each of them we split into heads, as I said. So we just split, like, let's say, query into heads. And what's remaining is the dimension of each head. So maybe there is 8 heads and I don't know, maybe 100 of these. So let's say like query has dimension of 800, so you have 8 heads. Each head has 100 dimension or size. And just to now summarize, so each token will have 3 vectors, which is query key value, and then those will be divided into heads, and each head will have it's like a vector of certain size. And there is some number of heads of those vectors. And then each head will, like, first heads will interact with each other, second heads of query key value will interact with each other, etc. And heads will be independent from each other. So only first will interact, only second will interact, but there is no first and second interacting together. Okay. We need to do some permutation here. So you see, I'm putting batch size to be the second one. I'm putting, so this is 0, 1, 2, 3, 4. So this is a bit confusing, number 3, number 2. But look at the indices. So I'm taking this dimension, which is the dimension that separates queries, keys, values, and putting that to be the first dimension. So now imagine, like, all of the stuff about queries here, all of the stuff about values and keys, and then keeping the batch size. There, this is a bit confusing. Maybe you're gonna need like some practice to understand this. You need some practice, yeah. And then separating by heads. Head is the next separation. And then sequence length. So imagine that we are separating by like, just take first head of each token and now put it in a sequence, like sequence of tokens. So first head of the first token, first head of the second token, first head of third token, etc. And then, so that's what this sequence length here. It just list of tokens. And number 4 is the head dimension. So that remains the same. So this is a bit confusing. Maybe you can copy paste this into ChatGPT, try to understand, visualize code. It will take some practice. So just know that we are separating by key query value and then by kind of heads. And in each head there is a sequence of tokens. And why are we doing this permutation? Well, first of all, we will get a list of keys, queries, keys, and values separated from this one long vector. And so now each of them will be batch head, and then within head dimension you have sequence of tokens and size of the head. So it makes sense to separate keys, queries, values. You need them separated. Now this, I think I messed up. I need to delete this as well, I think. And we will apply rotary embeddings or rotary positional encoding to queries and keys only. And we need to transpose swap these two before we pass them through rope, because that's what this rope expects. So it expects batch, sequence, head, and head dimension. That's what it expects. So that's why we need to swap it. Batch, sequence, and then head dimension. Let's see. You see, batch, T is time or sequence length, head, and then head dimension. That's what it expects. So that's why we transposed and passed through rotary and then transposed back to return it as it was. So I had a bug here before, and some person fixed it, and then my large language model worked a lot better. And finally, this will do attention mechanism. So we're not gonna go ahead and code attention from scratch here. You can watch Andrei Karpathy video or million other videos on coding attention mechanism from scratch. That's the most explained thing in AI research, I think. So I'm using this because it's very fast. Usually you want to use these like PyTorch native things. They're very fast, they're very good. The engineers that build them are very good. You only want to build stuff from scratch if it doesn't exist in PyTorch. So passing query key value is causal, means tokens are only looking at the previous tokens. They cannot see the future tokens, which is what we want in large language model. Dropout, if it exists. That's so easy. Just calculate attention. It's very fast. It's very good. Okay, so then attention output, we're gonna transpose something. Let's see what we're doing here. Okay. So attention output will be same shape as our input, which was batch size, sequence length, and then token embedding dimension. But here we will actually have, instead of token embedding dimension, we will have value dimension. Because at the end, we will just have all of the sequence of tokens, but values for each token, not the token embedding itself, but the values for each token. But in this case, value size is same as the token embedding size, so it will be literally same size as the input X at the beginning. And now, as I said, for each token, we need to convert the value. And remember, this value also contains like added values from every other token as information, but we need to convert that value for each token back into the vector embedding token. So we will do that by simply passing that list of values through this output layer, which will convert list of values to list of tokens, and the shape will be same. And let's just understand this transpose and reshape. So transpose will do the same as here. It will swap head dimension and the sequence length dimension. So this is what we will get. Originally, this attention output is actually this shape, which is batch head sequence head dimension, okay? And then this transpose will swap head and sequence, so we will get batch sequence head and then head dimension, so number of heads, head dimension. And then we will combine number of heads and head dimension using this reshape. So it will automatically figure out, so sequence and batch are gonna be the same because they are at the same place, so it will not be changed. And then it will figure out that it needs to combine head times number of heads times head dimension to get this size, so it will merge those two independent. Now all of the independent heads for this value will now get merged into a single value vector. And so now we have this shape, batch, sequence, and D model. So this is list of values, enriched values with other context, and then we pass that through output to get list of actual tokens. Next, we have the simplest part of this whole file. So we're just gonna be the transformer block. Let's see what this is. Initialize. We have D model, number of heads. This is the expert, mixture of experts. So the expert hidden dimension that was 4 times bigger than the dimension of the model, if you remember the feed forward of the expert. And we'll see what this is for rope. I think I'm not using this. We'll see. I forgot if I'm using this later. So this LoRa rank is for different implementation of DeepSeek's multi-head latent attention. I forgot to delete it. So I think you don't literally need any of these. We'll see later. Sorry, I forgot if I use this or not. Okay, we got max sequence length. You need this. Number of experts. You need this. Top case, selecting top 2 experts and 10% dropout. Okay. Starting with the initialization of the superclass. And superclass, I mean like this NN module. You want to initialize that within init of this class. Okay, first initialize our attention, multi-head attention class, passing the necessary parameters, the model number of heads, max sequence length dropout, and then mixture of experts. I'm gonna save that as feed forward. You could also save it as .moe instead of feed forward, but just pass in the parameters. And then normalization. So we're gonna use RMS norm. You can watch this video RMS norm from scratch. I explained everything here, link below. So that's normalization to keep the numbers from becoming too large, like, or too small, like 1,000, 10,000, million, or 0.0001. We want to keep numbers around number 1. So that's what normalization does. We're going to have 2 of them. We'll see later why. So dropout as well. And let's see the forward for the transformer block. We're going to pass through attention, but first normalize. So if you remember, I'll show you the architecture of transformer. You first normalize and then pass through attention mechanism, this input X. So looking at this decoder part, looking at this attention mechanism, this norm goes after, but people figured out you should put norm before. It works better. And here in feed forward, we will also have norm before the feed forward. Now in decoder only transformer, we don't have this cross attention part. So we just have attention and then directly to feed forward, and norm is before feed forward and before attention. So after we pass through attention, there is a residual connection, which we'll see. So attention output first goes through dropout to regularize, okay, and then residual. Okay, I can't say regularize, regularize maybe. So this is that residual connection. So we add the output of the attention plus this input. So the idea is that we want to also preserve some information from the tokens themselves, not just process them through attention, but also preserve some initial information as well. So as I said, when you add 2 vectors, it's adding information from both of them. So from the original and from processed. Next, same thing, but through the mixture of experts. So we have this X that just came out of this, pass through norm first, and then through feed forward, which is our mixture of experts. And that's gonna return not only the output, but also this auxiliary loss. And then regularization and adding the residual network to preserve some of the information from before this feed forward. And then return processed X and auxiliary loss. Next, let's combine all of this into a large language model, whole large language model. This is also short part. I think it's very simple. The most difficult part was the experts, and because I never explained it in different videos, so I explained it here. So now this should be easy. My file moe.llm.py disappeared for some reason. And I also have this init.py. I don't know how it got created, but anyways, you will actually need this. We're gonna create this later, so don't worry if you don't have it. But make sure to have this file, moe.llm, moe dash or underline llm.py. Let's first import this good stuff. So from typing optional configs.moe config import moe model config. We don't have this defined yet. We'll make it. And from models.layers import moe transformer block, which we just created. And so let's create our large language model. So I named it MOE minimal LLM. Maybe could have given it better name. It's like a small mixture of experts or minimal mixture of experts LLM. And so we're gonna initialize this config with the class MOE model config. This is the class that we will import. Later we will define it. And do the super initialization. And so the config that we pass, config, I'll show you what config is. First, let's see. Okay, yeah, here. So token embedding, it's gonna be equal to nn.embedding. This is a big matrix of token embedding. So each of the tokens in the vocabulary. So we have, let's say, 200,000 possible tokens. And if you don't know what tokens are, watch my Llama 4 from scratch course in the description below. So tokens are these like sub-words that model is predicting the next token, generating. And so we have this big dictionary. It's like a dictionary, or it is literal dictionary. I'm not sure if it's literal dictionary or like a dictionary. But anyways, it's vocab size, so 100,000, 200,000 tokens. And for each token, it has vector embedding. So if for example, token car can have some vector embedding, and it's maybe at position 70, we can just index into this dictionary with position 70 and take out this token for this vector embedding for the token car. But we'll see maybe, this is commonly explained everywhere, so I'll just go quickly through this. We're gonna do some dropout, position dropout. We'll see later on an example. I'm gonna show this through an example. Now we just created we defined transformer block that has attention and feed forward. But large language model will have multiple of these blocks stacked. So tokens first go once and then go back and repeat and repeat and repeat and repeat. So we're gonna create a list of these blocks, each block having attention and feed forward. Okay, so it's gonna be array. And then in that array, you're gonna say MOE transformer block, which we just defined earlier, and pass in all of the stuff it needs. Model dimension, head dimension, feed forward, hidden layer. As I said, we'll see later if we need these or not. I think we don't need this one. But anyways, let's have this. This is, what is this? I forgot. We have this. It's not good if you don't know what your variables are. But I think this is used for the DeepSeek latent attention, so we will not need this. We don't use this anywhere. You see, it's only defined once in this whole file. Max sequence length, number of experts, so all of that will be passed through this configuration file. So when we are creating large language model, we're gonna put this configuration file separately. So we can have multiple different large language models. We don't need to hard code any single one into these files. These are just like components, layers, and stuff. Okay, so do this for the number of layers. Big language models, I think they have 30, 40 layers. Smaller ones have like 15, 16. But absolutely huge ones, who knows how many they have. These like Grok 4 and stuff. Sorry, you don't need to change anything else here. Next, let's define normalization. and dropout. And this is for the output head. Now, output head is a separate thing from all of these layers. I never mentioned it until now. Let me pull up the architecture. So these are the layers, the green ones, and it gets repeated many times. At the end, we have, after all of the layers are repeated, we are generating the next token at the end. We're not generating next token within this attention and feed forward. Here we're just processing the current tokens in the context window. And after that has been processed many times, we're gonna take the last token in the context window and convert that to the next token using these, let's say these two things here, linear and softmax. So this linear is output head. We call this output head, and it's interesting. It can be absolutely huge. It can be 1/3 of the entire model. So how many times are you repeating this? 16 times all of these things. And just this one single linear layer can be like 1/3 of the entire model. And you'll see why, especially for small models. So output dropout and output normalization. Now we are tying, okay, so this is the output head. So what output head will do is it will take the last token size, and convert that to a vector that's length vocab size. So how many tokens do we have? That's the length of this vector. And that vector will assign score for each token. That score will tell us how much this token should be the next token. It's not probability, it's like maybe affinity. Like let's just say, like the bigger score, the more this output head wants that token to be next token. But the score doesn't have to add up to 1. It's not probability distribution yet. Okay, let's just now summarize. So LM head, output head, converts the last token that's now highly processed into distribution or scores for every single possible token in the vocabulary, how likely it should be next token. But again, we're not talking about likeliness yet. It's just scores. And we will use softmax to convert these scores to probability distribution that adds up to 1 to 100%, to now to convert scores into probability for each token later. This is one trick that people found out. You actually want to have same weights of this LM head as your token embedding weights. So it's gonna be the exact same weights for this linear layer. So what we are doing, these weights are actually token embeddings themselves. So we are taking the last token in the sequence, in the context window that person is saying, and multiplying that token embedding with every single token itself, like the embedding of every single token in the vocabulary, like 200,000 of them. This enriched last token that's enriched with the context that's processed through all of these modules, multiplying with every single token embedding, and that's gonna create the logit. So people found out that tying the weights like this works well. So now the weights for this output head are same, like literal learned token embeddings. And then this self-apply, self-init weights, here it will just initialize all of the weights. So embedding layers, linear layers, RMS norm, MOA transformer blocks, and all of the weights according to this rule, init weights. That doesn't exist here yet. So let's define it. We're gonna check which type of weights we are initializing. So if it's linear weights, we're gonna initialize weights. Let me see. Yeah. So normal distribution. We're gonna initialize weights with normal distribution with mean 0 and standard deviation 0.02, and the bias will be just 0, all zeros, if bias exists. And if it's embedding and not linear, so if it's embedding, we will just initialize normal distribution of mean 0 and standard deviation 0.02. Next, we will create forward pass, define forward pass through this large language model. Let's see, Gemini has good explanation here. X is just all of our input, which is batch, sequence, and then it's actually just a list of token IDs. So it's batch and sequence of token IDs. And we will see later how we get this list of token IDs. And if we put all of those IDs through this token embedding that we actually defined just earlier, we will convert each ID, or we will exchange each ID with its token embedding for that token. So for example, if token cat has ID 3050, we will first pass 3050 as this ID. We will see later, we didn't code that yet, but now imagine we have that ID, and then by passing X through this, we will, instead of 3050, we will get the whole token embedding for the cat, and we will multiply with the square root of the model dimension. And now that I'm looking at this, this was used when you are adding positional encodings to the token embedding. But we are using rope, so maybe we don't need this. So maybe I'll leave this here, or I will delete it. I'm not sure yet. Let's leave it as is. This was meant to increase the embedding vector, because when you are adding position vector, if position vector numbers are a lot larger than embedding numbers, then it will kind of drown out these embedding token. It will all be like position information because those numbers are very large. So you want to increase the size of these numbers by multiplying, but that was when you were adding position vectors. But now we are using rope, so we are rotating the embedding token embedding itself. So maybe we don't need this, but let's leave it for now. This position dropout X will zero out some dimensions within the token embedding vector. So imagine you have this token, hello and world. It will randomly turn some of the dimensions within the world token to 0. So dropout is to regularize, so the model doesn't get too dependent on these exact embedding for this, like numbers for this embedding. It improves the general ability. Next, collect auxiliary losses from MOE layers. So we will initialize it at this empty array, and for each block we will pass our input through the block, and the block will return the processed input and this auxiliary loss. And if the loss is not none and this auxiliary loss return auxiliary loss is true, we want the LLM to return this array of auxiliary losses for each block. And output projection, so after we pass throughout all of the blocks, each block being attention plus feed forward, we're going to generate the next token here. So when we pass throughout to LM head, we will first normalize the X and drop out X, and then pass through LM head to generate the next token. As I explained, LM head will convert from the token embedding, which is the last token in the context length, in the sequence, in the conversation, to the logits or scores over entire vocabulary. Each possible token gets a score to be the next token. Combine auxiliary losses, so we just sum all of them. So we first collected them because we're going block by block. So we collected and then summed. If it's not none, and if we want to return, then we will return logits and auxiliary loss. So I guess we could also just sum them here as opposed to first putting them into array. I think that would also make sense. Or just return logits if we're not returning this. And that's it. So logits is like scores for every token in the vocabulary to be the next token. So we just have like maybe 10 more lines of code in this file because we finished all these 3 big files. So you need this file that's __init__.py. The purpose of this init.py is to have a clean API, clean way to import to different scripts. So without it, we would be importing like this, like my package, which is gonna be our models.components, from models.components import, from models.layers, from models.moe. But with this init.py, we can actually just say from models import all of these. So we don't need to say dot and then file as well. So it's a lot cleaner. We can also say from models import everything, all of the classes here. Here we wanna just export all of our classes so we can easily use them in other files. Let me show you what I mean. So first we will import from components. We will import expert, top K router, mixture of experts. And from layers, we will import all of our classes, although we don't have multi-head latent attention. I did not code that, so I'm gonna delete this just a second. And from MOE LLM, I'm gonna import MOE minimal LLM. And then we will export. First, we will define this all array. Expert, so we will just put all of these classes that I just imported. And that's it. So this is how we will use these classes in different files. And multi-head latent attention doesn't exist, so I'm gonna delete that. Make sure to commit everything to GitHub. Next, besides this models folder, let's create a new folder, optimizers. I'm separating it because we're gonna be doing research on this, but you can structure it differently as well. And inside we're gonna have __init__.py and muon.py. So Muon optimizer. We're gonna define Muon optimizer ourselves, and Adam we will just use from PyTorch. As I said, you wanna use everything you have in PyTorch. Those are very fast, the best things, unless you wanna code it yourself and change it. Now, I don't know if there is a single video on entire YouTube about Muon optimizer that's well explaining it. If you go to my channel and search for Muon, I have videos about Muon, but I don't think there is a full course on Muon optimizer anywhere on YouTube. Maybe you can also search for YouTube. Search for Muon optimizer. Maybe this one is actually good. Yeah, this one is good. So it's maybe more complex if you want to watch it. I'm going to try to summarize Muon as well. In the muon.py, import torch and functional as f. And then we're going to torch compile whatever we define here. So 0 power via Newton-Schultz 5. That's how Keller-Jordan defines it. And this is the tensor that we will pass through this function, and 5 steps. We'll see what those steps are, and it returns tensor. We'll see what it returns. So Newton-Schultz iteration to compute 0th power orthogonalization of G. It's crazy. If you do Google search for Muon optimizer, there are my videos here as well. The main idea behind the Muon optimizer. So you have a matrix of weights in a neural network. So weights for the first neuron, weights for the second neuron, third. So this, when you multiply input with these weights, you get some hidden layer or some neurons, some activations, whatever. And so you multiply. So I'm just explaining neural networks. So input times the first row of weights gives you the first neuron. Input times second weights gives you second neuron. There is also maybe activation function in between, so just before the neuron. That's not so important. What's important is that this weight matrix, if you look at each row of this matrix separately as a vector, if those vectors are perpendicular 90 degrees, so let's say this, the first row vector is this, the second row vector is this, if there is 90 degrees between them, neural networks learn faster with less data. Why? I don't know if anybody knows. Maybe the inventors have some idea. I'm not sure. I haven't read about it at all. I'm actually trying to keep up with Muon Optimizer, and I haven't understood why neural networks learn more with less data if this rule of perpendicular rows of the weight matrix or columns, it can be rows or columns, if that rule is true for the weight matrix. So Muon Optimizer, we're trying to keep the rows of the weight matrix perpendicular to each other, if we look at rows as vectors. The way we will keep the matrix orthonormal, which means that either rows are orthogonal to each other or columns are orthogonal to each other and rows or columns are normalized. The way we will keep it like that is we will each of the update matrices. So you know there is this update matrix which is gradients. So this is the classic backpropagation, and I showed you my course on backpropagation from scratch. So when neural network does backpropagation, there is this update matrix. It's like for each weight how much to add or subtract from the weight to make the loss go down. So the update matrix gets multiplied with learning rate and subtracted from the current weights of the model to adjust the weights. So again, update matrix is made from gradients. It's like how to change weights, what to subtract from weights to make the loss go down. And it has same shape as the weight matrix. And so we're gonna make these update matrices orthonormal, and then as you just add them, then the weights themselves will be orthonormal because all of the matrices that made the weights are orthonormal. But we will make it approximately orthonormal, these update weights matrices, because the true orthonormalization would involve calculating singular values and singular value decomposition, which is very expensive and slow. So we will approximate singular value decomposition operation with some kind of polynomial. So to me it looks like a polynomial. Let's see. First of all, we will apply Muon only to 2D matrices. It's made for 2D matrices, not embedding vectors, not normalization that are not 2D, so only for these 2D weights. And as I said, we have these coefficients here. And this is first reason it reminds me of a polynomial. You'll see later that these are coefficients in something what looks like a polynomial. So we will convert G to this half data type because this algorithm is stable enough to do this in FP16 and it provides a lot of speed up as opposed to being FP32, for example. Then we're gonna check if the matrix is tall, and so if it has more rows than columns, so it's tall. If it's tall, we wanna make it wide. We wanna transpose it. The algorithm works better or is standardized on matrices where number of rows is less or equal than number of columns. In the next row, we have normalization. So x is equal to x over, and then x dot norm
along these two dimensions, and then to avoid dividing by 0. So Newton-Schulz iterations, which is our polynomial approximation of this singular value decomposition and making the matrix. So this is what makes the matrix orthonormal. And it's gonna diverge if its spectral norm, largest singular value of the matrix, is too high. So larger than this value. So we are dividing it by this norm to make sure that the matrix is small enough so it converges. Or the spectral norm is small enough, I should say. So this -2 and -1 are rows and columns, and it will make sure we calculate the Frobenius, whatever the norm is, of each matrix individually if there are multiple matrices, or if there is one matrix just of that one matrix. So if we have a single 2D matrix, standard case, let's say it's like this. This is the norm. We square all of the values and then square root. So that's the norm. And the norm among these dimensions is also the same. But if we have multiple matrices, then it would actually add up all of the numbers of both matrices. And putting it like this, it will now separate so rows and columns, and then rows and columns as well. So two matrices. And we also have this keep dim equals true. So let's see what that does. So our result is 1D tensor. The first norm for the first matrix, the second norm for the second matrix. But our input was 2, 2, 2. So our input, this was 2, 2, 2. But our result is just of size 2. And you cannot divide this 2, 2, 2 with or by this 2. So you need to reshape it to 2, 1, 1. But we don't need to reshape it if we just preserve all three dimensions. So we just say keep dim equals true, and then that will preserve. So for this matrix, for this matrix. And now PyTorch can divide this. It can divide the first matrix with the first norm and second matrix with the second norm. So after we did this normalization, stabilization, this is where we come to the point of this polynomial approximation that I was talking about. So I'll just show you the lines of code. So we do some number of iterations, and every iteration we make the matrix A, sorry, I should say this X, matrix X, that is our update matrix, we make it more and more orthonormal every iteration. So 5 iterations, we make it more orthonormal. 10, we make it even more orthonormal. The question is how many is enough. We don't want to waste compute. And this is something I'm also testing in the paper that we are writing here. So we're going to try different number of steps, 10 steps, 5 steps, 2 steps, etc. But the default is 5 steps. So look at this A. A is X times, or X matrix multiply X transposed. If X were perfectly orthogonal, A would be the identity matrix. Let me first show you the other lines of code, and then we will discuss. So here, this is why I say it looks like polynomial. So if you look at this A, you have literally A, like something that reminds of A squared, which is just matrix multiply in this case. So A, what this reminds of a square, times this coefficient, and then A to the first power, what reminds of A to the first power, or times coefficient. So that's the B. And then this is a bit weird. We have b times x, but then we have also just x times the third coefficient. So that's why it kind of reminds me of polynomial here. And it literally is polynomial. So it computes the polynomial using the coefficients b and c. This calculates terms based on x times x transposed and x times x transposed and squared. So we are talking about this one. And then in the next one, it combines the original x with the polynomial corrections. So polynomial corrections and the original x. So this second part, look, you have x, the matrix, the update matrix, and you are transforming it to be more orthogonal with this b. But you are also keeping some of the old x with this a, because this is just a scalar coefficient. So a bit of old x plus a bit of new x, and every time this will be more and more orthonormal matrix after every iteration. So this is very fast to do. Look how fast it is. It's just plus and multiplication. Very fast matrix multiplications on GPU, as opposed to slow singular value decomposition that needs to run on CPU only, I'm pretty sure. Okay, like this is a bit tough. So this b constructs the coefficient for the x to 3 and x to 5 terms. I guess I need to make like a full video or figure out a way how to explain this muon better and how to understand it better myself as well. But as I said, what this does is it makes this gradient, like a vector update matrix, more orthonormal with each iteration. And so if we transposed the matrix here, we're gonna turn it back and just return this now matrix that's a bit more, that's orthogonalized or approximately orthogonalized. Then we define class Muon, which is the new optimizer inheriting from Torch Optim optimizer. Momentum orthogonalized by Newton-Schultz. That's what we are doing. And init, so parameters of the model. Learning rate is quite high compared to Adam, which is usually 0.01. So 20 times smaller than this. We're gonna be checking this momentum. I'm gonna be doing ablations. 0.9, I find it works very well in the experiments. We'll see later. Number of steps here, number of Newton-Schultz iterations, 5 by default. And using or not using Nesterov momentum, we'll see later about this. Oh my god, what is this? Then this default is equal to dictionary. This will just package the hyperparameters. You see, just packaging hyperparameters into this defaults dictionary and initializing the superclass. Next, torch no grad, and then we are defining some step. The reason we don't want torch to calculate gradients here is that we are not gonna be training some weights within this optimizer. We are using this optimizer to train the neural network, but we are not gonna be calculating gradients and updating whatever this function does. We're not gonna be training this function itself. This function is just used to train other weights. Then we will just loop through parameters. We'll check if parameters have gradient. If it doesn't have gradient, just continue. And so we will get the gradient. And here this state, when passing parameters, we get the momentum that's saved here. So if we don't have momentum buffer in state, Then we will initialize it from zeros, and it's gonna have same shape as these gradients for this whatever the parameters we are processing now. Then we're gonna store this momentum buffer into this buff. So it's gonna be either like zeros or it's gonna be whatever we had previously. For the next line, we have buff.lerp linear interpolation. We have the gradients and then 1 minus the momentum. So it updates the buffer in place, okay? Because we are just using it .lerp here. It's like saying buffer is equal to buffer times momentum plus gradient times 1 minus momentum. So remember that our momentum is 0.95, so it's very close to 1. So that means that a lot of the old 95% of the old buffer will remain, so the new buffer will be 95% old buffer, and just 5% will be the new gradients. So gradients will not change so much this buffer, which provides stability. Because gradients can be a bit random. We don't want gradients to change stuff so much, so we just want it to change bit by bit. This creates an exponential moving average of gradients. So the reason we need moving average is, imagine these gradients are on average pointing in some direction on the loss surface that reduces the loss. But each gradient individually will be pointing in a bit random direction as well. But on average they're pointing in the good direction, so that's why this, like calculating the average of the gradients, is good. So buffer will start from 0 and then based on the gradient and gradients it will average out and have this exponential moving average of gradients. Then, oh my god, again, we have this checking if it's using Nesterov momentum. So if Nesterov is false, then it will apply the standard momentum of the gradient just being the buff itself. So look, if we have Nesterov, then it's gonna be something which we will explain, but if we don't have Nesterov, it's just gonna be the buff. And then that buff will be, so that's just gonna be passed through the Newton-Schultz, so that buff will be literally the weight update matrix, which again, it's just the gradient itself, like exponential moving average of the gradients. But if we have Nesterov, then something a bit more complex is happening. The difference is that standard momentum takes 5% of the current slope current gradient, and Nesterov momentum takes almost 10%. Because you can see at this point that we are also linearly interpolating the buff and the momentum.
So you are literally taking the buff, which we had in the previous one as well, and then multiplying that with 0.95, and then giving even more of the current. So at the end, this way, standard momentum has only about 5% of the current gradient, and Nesterov momentum has almost 10%. This causes Nesterov momentum to look ahead at the future spot by taking this step, calculating the forward step, and then adjusting based on this forward step. And so it will calculate the slope at the future spot. So because we are going from 5% current to almost 10% current, we are simulating the correction we would have made if we had stepped into the future. I mean, did the next step. There is this video, Nesterov with momentum. I think it's very good. So then in the next line, we just make this gradient update matrix more orthonormal. with 0 power Newton-Schultz. And just one more line. So p dot add, and then we have this, all this good stuff. It looks a little bit complicated. This is the actual update of the weights. And it's complicated because it's designed to work based on if the update matrix is tall or wide, has more rows or more columns. This part will measure or check if our matrix is square, if it's tall or if it's wide. So if the matrix is tall, it has more rows than columns, then we want to increase. So this number will be larger. So if you look at this, this is rows over columns. And we're gonna get a maximum number between 1 and rows over columns. So only if rows is larger than columns, then this number will be larger than 1. So then only if there is more rows than columns, then we will have some number larger than 1, and then we take square root of that number. But that's not so important. I'm just trying to say that if we have more rows than columns, then this number will be larger than 1, otherwise it will be 1. So tall update matrices will make the neural network learn slower, and it's due to energy dilution. So our shape correction for tall matrices will be greater than 1. So we want to increase the learning rate, multiply by shape correction. So we want to make the learning rate larger for tall matrices because they are diluted. If we don't, then they will just cause the neural network to learn slower than if we had square update matrix or wide update matrix. Explaining why tall update matrices make the neural network learn slower would take me too much time for this video, but I will explain it in the future. For now, you would have to ask like Gemini or something if you want to understand this and study it yourself, but in the future I'll make it. Looking at our final formula, we have our weights, which is gonna be our p, the parameters. So p in our code here, we have p.add. So we are adding something. P minus this learning rate times orthogonal gradient. This is important. So we are literally modifying p in place. So here we are modifying p in place. We are just adding, well, in this case, we are adding negative learning rate. And so when you say minus learning rate, so that's going to be subtracting then. But it's going to multiply learning rate with this g. G is our gradient. So g, we are forcing g to be same shape as p. So it's going to be 2D matrix. And we will multiply it will multiply g times minus learning rate. And so it will add, or in this case, subtract it from the p itself. So we will have something like this. So that's gonna be the Muon optimizer. I'm gonna just commit this to GitHub and we can go on to the next thing. I will also create init folder here in optimizers, and inside I'll just import this from Muon, these two classes, Muon and 0 power Newton-Schultz. And I'm gonna export it like this, so it's easy to import just from this module optimizer. So I can say from optimizers import Muon, from optimizers import this. I don't need to say from optimizers.muon import this. And we can easily add more optimizers and then export everything from here, and it's gonna be very clean. We will be importing just from optimizers, everything we need. Then let's make a new file outside of everything. train_moe.py or train.py or whatever. Here we will literally write our code for training the whole neural network. So we will actually run this Python train_moe.py when we want to train the large language model. Let's start with some imports: time, OS, and torch, and then logging, and then from torch utils data import data loader for loading the data. Now we need to do this because it will just put a lot of warnings in the console when we are training the large language model about like tokenizing process being split. So you need to do this for it not to split the tokenizing process or something. I'm not 100% sure. Maybe this is if you have multiple, if you're tokenizing with multiple GPUs or something. Okay, from configs.moe config, we don't have this yet, but we will have it. Import moe model config. So we will create this soon. And from configs.dataset config, import data config. And from data.loader, import prepare LM dataset. And we will also have this, we will call this as well. From training.trainer, import train MOE model. From utils.helpers, import set seed. From utils.logger, import setup logging. Okay, we can print system info, like if it's using CUDA or CPU if you want. And so that's the device that we are printing. And if CUDA is available, you can also print which GPU it is and how much memory it has. And this will get the first GPU, which is, if you have just one GPU, it will be your one GPU that you have. And I can also print torch version. Set up the logger to output in just logs folder, which it will create automatically. And then logger.info starting MOE training. So this is just some information. Print system info, it's this function that we just made. So this is in main, this is when it starts training. And then set seed 42, we want consistent seeds so we can reproduce experiments. MOE model config. So this is what we imported. We will create this. So this will just give us all of the configuration for our model. And then we need to import dataset, download it from the Hugging Face. I'm gonna use this dataset, Hugging Face TB small LLM corpus. This is good for training small LLM. And this is the name. There are 3 datasets in this repository, so this is the one that we will use. And we will also use this tokenizer because it's made for this dataset. So now we will just set a sequence length from the config that we will create later, and number of documents from the config as well. How many we want to download. But we will be streaming, downloading as we train. We will not download the entire dataset at once. And then cache directory for this Hugging Face downloads. So make sure this cache directory is included in your gitignore. So it's not here. Maybe I can just add like this. So it's not committed to GitHub. You don't want cache directories committed to GitHub. Split documents before tokenization to prevent data leakage. So we are splitting between training and evaluating data. So from datasets, import load dataset, and I told you that we will install datasets with requirements. And so raw dataset, we'll just call this load dataset and pass in dataset path, which we defined here, data config, and dataset name, and the split dataset config.split. Do we have that? Maybe we'll have that later. Why don't I have that? We'll see. I'm not sure why I don't have that here. Cache directory. Streaming through. We want it to download as it needs. We don't want to download entire dataset because we will just train on very, very small part of the dataset. So we will just now take number of samples, maybe 10,000 documents from this raw dataset. You know, it's streaming, so it's gonna be streaming 10,000 documents. We will then take it, load that into memory after it's streamed all of them. And then we will take 10% of that number of documents to be validation data set, and remaining will be the remaining number will be the number of training documents. And from datasets import dataset. And so I'm just gonna take, so this is raw train, so datasets from list, raw samples, we're just gonna take from 0 to number of, or from the beginning to number of training dataset, that will be the training. And validation same, from number of training until the end. And logger, we can say that we split the data into training and validation and number of documents. From data.loader import setup tokenizer, tokenize and chunk, and finalize dataset. So tokenizer is gonna be setup tokenizer, which we will write this function, but we will pass in data configuration. And then config vocab size is equal to tokenizer vocab size. Tokenizing training set, so now tokenize and chunk from our data.loader, which we will define as well. Pass in the documents tokenizer config. Finalize dataset. We also created this function. I mean, we will create it later to see what it does. It does some processing on the dataset. And then tokenizing validation set. It's gonna be the same. And so we have now the tokens themselves. We can say length of those tokens for both. This is for data loading. From RAM memory into CPU, CPU will process the data, turn data into tensors, and then it will be sent to GPU, and GPU will perform multiplications. So batch size is how many of these different chunks of data are independently sent and processed. Better GPUs are gonna be able to take more. Number of workers is the amount of background CPU processes that are loading data and sending it to GPU. So if GPU is already processing one batch of data, the next batch is already being converted and loaded by the CPU, so next two batches actually, while this one is already being processed in the GPU. Persistent workers, once it finishes loop through entire dataset, if workers are not persistent, then that processes will be removed, but then it will need to start them again for the next epoch, for the next processing of the same dataset. So we will not actually be removing them and starting them again. There is no reason for that, because we are processing multiple epochs, multiple times over the same dataset if we are doing that. And this pin memory is data is put here for the faster access by GPU. Then train loader, validation loader. So these are gonna load the dataset, and we will shuffle the documents. So it doesn't train on the like some predictable. Maybe in the first part of datasets it's all like medical documents. So it's gonna just maybe learn like medical and legal documents, and the rest of the dataset we are not teaching has some math and other stuff. So we will shuffle everything to randomize the document order. This is just printing the information. Experts, so this is just prints, a bunch of prints. Starting training, we can measure time. Train MOE model. We have that here, we imported that from training trainer. And we need to pass in this, so we will define this, we didn't code this yet. We can measure elapsed time after we get the trained model and metrics. Training complete, results. Okay, I'll just go quickly through a bunch of prints here. Validation, perplexity, loss, accuracy. This is where we save the checkpoint. you can save that. Like it will create this folder, and make sure this folder is not in the, so it's in the git ignore. Okay, it's not in git ignore, so I'm gonna add it here maybe. So we don't want to commit these checkpoints to the GitHub. And then torch.save. So we will just kind of structure all of this information so we can later load it easier. So checkpoint path. Okay, so we are just printing where the checkpoint path is. And this is the main. Oh, so that's it. So when we call this with the Python, it will just trigger main, which is gonna start training the model, loading dataset, training the model. And that's it for this file. Let's create a new folder, configs, and inside let's do init.py, and next to that dataset underscore config.py and moe underscore config.py. Let's do dataset config. So we will import from data classes, import data class, from typing import optional, callable union, and import logging. And so we will just get this logger, logging.logger, and then do data class here and define data config. So data class will automatically generate some boilerplate for classes that store data. So you can later call some of these methods that are gonna be useful for working with data. So I'm quickly gonna go through this dataset path, which is gonna be our Hugging Face. We already did all of this: dataset name, split, train, tokenizer. I think we're gonna use different tokenizer, but this is default, but it's gonna be changed. Trust remote code false. I think this is this is not so important, none of this. Let's just go quickly. We have some defaults for sequence length, stride. So when you're training large language model, your sequence length, you train this data, your tokens, and then you move on to the next. So you move by the whole sequence length to get the next data, like next tokens. So I had a bug where I trained on this sequence, and then I moved just by one token, train on this sequence, and then train on this, which was a bug. My loss was 0.001, which is not good. That's how you know your loss is too low. That's how you know you have some bug. So when you train on this sequence, you move by the entire sequence of tokens, you train on the next sequence in the data. That's your stride. It's equal to the sequence length. Number of samples. Okay, I think this is not so important. Let me just do this. I want to go quickly through this. It's very easy. What this does is it just loads dataset. We have these optional parameters. Streaming true, we already talked about this. Save to disk, load from disk. If you want to save literally to your memory, so maybe you don't want to process dataset every time you run the training, which we will set this to true, I believe. And then we have some checks. Let me see these checks. Maybe not all of these are necessary. I mean, I think you can just copy this. So dataset path must not be empty. You need to there are these rules. I think you can just copy paste this from my GitHub in this file if you want. I don't want to spend too much time here. Let me see. Stride must be positive. So I don't know if we even need to do so many of these checks. We don't even need to do so many of these checks. You don't need to write this if you don't want to. Maybe it's good. If it's non-empty string, if it's not a white space. Let me quickly go through this. Okay, I think that's it. So we just have this config data class, and that's it. Now let's go to moe_config.py. So this is just config for our large language model. So we will again import data class, and from typing and define the data class. So dimension of the model, this is small enough to run on free Google GPU, I'm pretty sure. We'll check it later. Number of heads, this is good number of heads, number of layers. So these are large language model layers. Hidden dimension should be 4 times this. Now, is this 4 times this? I think it's more than 4 times, but it's okay. We can just check with this, we can check with different. It doesn't have to be 4 times. Let's keep it like that. Here, we are not using these in our large language model, so maybe you don't need to actually write them. This is for DeepSeek, and this one as well. So maybe you don't need these 4. If you want, you can leave them there. As I said, it's not good if I don't know what the variable does, what the variable is. I think this is also for DeepSeek, because this was done by some other person. They added DeepSeek multi-head latent attention, so that's why I'm not sure what this is. Batch size 24. I think you usually want to keep these numbers powers of 2, but sometimes you just don't have enough GPU memory. Maybe batch size as well. Okay, maximum steps 1000 is maybe low, but maybe if you are testing, maybe just 50 to 100 to you do 10 steps to see if you have any bugs. Then you do maybe 200, 300 to 500 to test a bunch of different experiments, and then 1000, 2000 to test deeply the best of those experiments. You want to test them even more with maybe 1000 steps then. But you put 10 here just to check for bugs when you're running the large language model training for the first time. Gradient accumulation, that's simulating batch size. So if you cannot load too many batches into memory, then you will just do multiple times without updating the weights, without doing backpropagation. You will just update the gradient, accumulate gradients multiple times, as if you have larger amount of samples, larger amount of conversations. Muon learning rate, this is from the experiments that I did. Momentum 0.9. You remember that the default is 0.95, but through our experiments that we will do later right in this research, we will get that for our setup 0.9 works best. Adam learning rate, this is all from the experiments that we did. Max sequence length 512. Number of documents, maximum tokens that we want to load from the dataset. Evaluate every 10 steps. Maybe you can increase this. Wait. I'm not sure what this is. Wait, evaluate every 100 steps. So what is this? I forgot. I'm not sure. Why is maybe this is we're not using this? I forgot about this. Okay. Weight decay, regularizing. These are just regularizations. Use automatic precision, true. Let the PyTorch speed up the training. And then vocab size and logging milestones is just for logging. And then MOE specific number of experts, choosing top 2 experts, load balancing weight, which we talked about in the first part of the video. And then when we initialize, we just need to check that dimension of the key and query and value. Sorry. The head dimension is divisible. So you want to make the token embedding vector, or which is also the dimension of the model, divisible by number of heads. And it needs to be equal to head dimension. So now in the init, we will just export it nicely. So import MOE model config and data config from what we just defined. And then just put it like this, so you can import all of this from configs. You don't need to import it from these files. And that's it. Now let's go here. We can commit this to GitHub, save and commit. let's make a new folder, data, and inside we want to make dataset.py, loader.py, and streaming dataset.py, as well as __init__.py. So let's go to dataset. In the dataset.py, let's do some imports from Torch utils data import dataset, and let's create this class, text token dataset, and it's gonna inherit from dataset. Token dataset with configurable stride for creating training windows. Arguments are tokens, list of token IDs, and sequence length. And then stride showing like, so all of the tokens, we wanna take this sequence and then this sequence and then next sequence. So stride will usually be equal to sequence length, but it doesn't have to be. Here we will make it more adjustable maybe. So as I said, stride is by default gonna be the sequence length. So it's non-overlapping window. So you take this set of tokens and then the next set, the next. If stride is half of the sequence length, then it's 50% overlap. So you take this, then you take 50% overlap, then 50% overlap. And then if stride is 1, that's maximum overlap. They're just moving one by one tokens, which is actually a bug that I had. But depending on what you're doing, you may actually even use this. And so initialize this class with tokens, sequence length, and stride that I just explained, and set these two variables. Set stride, it should be sequence length if it's not defined. So default is sequence length. Calculate number of samples based on stride. So how many sequence lengths can we get based on the stride and the available tokens? And so we have like this length, which will just return number of samples. And then we can also get item. If we pass in index, we will just get this sequence length based on the index. So index times self stride. And you see, when we have a sequence and we're training the large language model, we want to predict always the next word. So the X will be this sequence, but in that X, we will go token by token and then try to predict the next word. So you see, X will be this, X will be like from the starting index to a starting index plus sequence length, but this will not include the last token. So that's our data that we have, and then what we're trying to predict is Y. And Y will be from the second token, so starting index plus 1, until the end. So imagine that our data that we have is like this sequence, and except the last, and the Y that we are trying to predict is the same sequence, but just moved by one token. So what that means is, if we have just first token in X, we are trying to predict first token in Y. Then we will have first and second token in X. We try to predict the second token in Y. First, second, third in X, trying to predict third in Y. So you see, it's like we're always trying to predict the next token, and that next token will be like same index as the last token in X that we have. So we will look at all these and try to predict the next. So that's actually the entire dataset class that we need. A text token dataset that's gonna split our stuff into sequences. Now let's go to loader.py in the dataset. We're just gonna do some imports, like annotations, and I'm just gonna do these imports quickly. You can just copy them from the, we'll see later how we use these. Getting the logger, setting up setup tokenizer. So we will load the tokenizer and we will pass in the tokenizer name. So this will just load tokenizer from the GitHub not GitHub, Hugging Face, and we will usually use that small LM tokenizer. And now we need to set the pad tokenizer to be equal to end of sequence tokenizer. That's something people do. And then return tokenizer. Load raw dataset. So this will just load. So load from disk. Because we saved it, we processed it or we downloaded it and we saved it. Now, if it's streaming, we're gonna load it a bit differently. So I forgot to say, if we want to load from disk, then we load from disk. And then we can also load dataset from the Hugging Face as well. So we talked about these. If it's like we talked about this stuff, so I can go quickly here. If we give some wrong name for the dataset, we may throw an error here, and then we will just return that dataset. Apply sampling and filters. The definition is a bit longer here. So is streaming, depending on if we have this iterable dataset. That's how we know if it's streaming, because this is just like iterator that we can materialize. That's how it's streaming. If config.number of samples exists, and if it's streaming, then we will take first number of samples. So just with this dataset.take, like 5 samples. So this will materialize that iterator. And otherwise, if it's not streaming, we will just take the minimum number between either number of samples or the length of entire dataset. So if we actually have less samples in the dataset than we want, number of samples, then this will throw a warning that there is not enough samples in the dataset. And we will just materialize this number of samples. So here we have some pre-processing functions. We can just apply whatever pre-processing functions we have. We'll see if we have any defined in the config. We can also apply filtering functions if we have any applied or any defined. Sorry guys, I made a mistake. So I made this file. This file is unnecessarily too complex. I worked on this and some other people worked on this. So I think you should just copy paste, because there is no point in explaining all of this. This is not so useful for your research. So just copy paste this file, and next time I'm gonna make it a lot simpler. This was my bad. So this loader.py. So in init, so in the data init.py, let me just define, import these classes that we defined, and then just export them like this. Now let's create a new folder, utils, and inside let's create a new file, helpers.py, and besides that let's create logger.py. Now I want you to just copy paste my helpers, or if you can code it if you want, but I'm just gonna copy paste this from the GitHub. So in utils helpers, oh no, that goes into helpers. So this is just set seed and count parameters. And then let's go back to logger. And let me copy this one as well. This is not so important for your research. You can just copy, you don't need to understand. I mean, you can maybe change it a little bit with AI and stuff, but it's not so important for you to understand. And then let's create a new folder, training. And inside, let's create trainer.py and evaluation.py. Maybe this could be evaluator, maybe, but I named it in evaluation, so Let's name it like that as well and create initpy. Guys, let's be fast here. There is a lot of boilerplate code, so I don't even know if I want to encourage you to code this step from scratch, like by hand, or to copy paste. I'm not sure. So you can see, so there is a bunch of imports. You can maybe just copy these, like so many imports from everything we've defined. And this trainer is for training the LLM. So early stopping is the class. So if it's training, and now suddenly valuation loss starts to increase, we will just stop the training because it's a sign that it's starting to overfit on data or something. So we will just have a bunch of this stuff. I think this is not so important for your research. This is just the class that you would usually copy paste. It's not, I don't know if I want to encourage you to spend time understanding this. So what it's doing is it's checking the best loss, and if 3 times the loss is worse, so there is no new best loss 3 times in a row, for example, or whatever the patience is, then it means like 3 times, like, okay, there is no loss, is not improving, let me just stop the training, which we will use later. So you have this counter and check if it's larger than patience. And then set up Muon optimizer. You know, when we coded Muon, we want to set 2D matrices to Muon. So, and we don't want like normalization and token. We don't want them in Muon. So just 2D matrices, so weights. So those will be Muon parameters, and the other ones will be Adam parameters. So you can print the amount of Adam and Muon. And now we are initializing Muon optimizer, which we coded, and Adam as well. Torch optim Adam W. You can check my video here. Adam optimizer explains step by step. So you will learn like the math and the theory behind Adam here. Link below the video. Let's continue. So we will just return these 2 optimizers in array like this, and then train the model, all of the parameters that we talked about, scheduling for learning rate. We want learning rate to start low and then quickly rise, because in the beginning updates will be a bit random because it doesn't know anything. But then it will quickly rise because large language model will quickly learn. In the beginning it learns very quickly. So we want to achieve maximum learning rate early and then slowly reduce the learning rate for the rest of the training. Because as it trains more, we don't want to keep updating more and more the weights. We don't want to keep updating more and more weights because it already knows. So we want to be more and more careful and conservative of how we change the weights, because towards the rest of training it already knows well. I talked about all of this good stuff. Here is describing. You can read if you want all of the inputs. The output is model, final metrics, metrics history. I'm gonna go quickly through this. I mean, this is we've kind of talked about this. So this is gonna train the model. We can like write this bar in the console if we want. We don't want early stopping. So, by the way, I don't know if I should still explain everything step by step. Maybe some people will find it boring. Maybe I should, maybe I shouldn't. Tell me below. I don't know who's even watching at this point. Okay. So as long as we are still training, as long as we didn't reach maximum steps, we're gonna be adding data, and we have this attention mask. Let me see. Okay, so we are just defining stuff here, and then we're pushing these to GPU, like the tensors, which are batches, which is our actual tokens and data, and then forward pass with automatic precision. We have cross entropy loss, we have shifting labels. So you know that, well, this is the X and Y I was explaining. We want to make sure, first of all, that these logits are contiguous in memory next to each other. So this is, logits are like like not scores for every token in the vocabulary, which token should be next, what the LLM thinks. Okay. We also need to adjust total loss for the gradient accumulation steps. And if we have this auxiliary loss, then we will add that to the total loss. So this is the mixture of experts loss. And then we can do backward, because we did backward here as well. We did backward here depending on if we have this auxiliary loss. Use no, it's depending on if we are using automatic precision. So here we also have auxiliary loss as well. And make sure to scale back the loss from automatic precision when you're doing back propagation. Optimizer step, let's see. Okay. We will just use the Muon and Adam optimizers. So for each of the optimizers, we will just unscale and then do the step 0 gradient. So this is contained in my course AI research from scratch about zeroing gradients or neural network from scratch. I also have that video. And then logging what happened, loss and accuracy and stuff. And then we can evaluate as well. And then printing whatever we evaluated. And then updating next step. And updating the bar in the console every 20th step. And final evaluation of the model after it has trained. Remember that we are doing cosine decay on the learning rate. So we need to get the current learning rate. Total time. So we are just printing a bunch of stuff here. Saving into output direction the metrics. Directory, output directory. And plot training metrics. So this is just about plotting and saving. So this is, let me go quickly. This is just about drawing stuff with the, I think you can copy paste this because it's not, like you don't need to do research with this. This is just for plotting. And then train MOE model. So we will initialize the model, set the seed. Now call everything we initialized above. Print, setup optimizers, schedulers. We have warm up for the learning rate, which is going to be some percentage, like 10% or 5% of the whole entire, like all of the steps. And we're going to write the logic here. So this is just the learning rate scheduling, the logic. Okay, and then train model, we call that, and that's it. That's it for the trainer. Again, guys, tell me in the comments below if I need to, or if I should explain everything. I can explain. I don't know if it's useful or if people will watch or if people care so much about if I explain everything step by step. I'm thinking like I just need to explain like the research parts and not this like boilerplate. And then in evaluation.py, we will just evaluate model. I have a bunch of imports. We will initialize these things here before we evaluate, and we don't need gradients. We will just get the data. Let's go. Autocast to CUDA, the floats. This will be automatically managed, and then doing the logits from the model, because model will generate the logits. And oh, wait, that's it. In init.py, we will just export all of this. So let me save everything. Let me commit everything to GitHub like this. And let's finally create experiments folder. Okay, and inside we can create Muon underscore versus underscore Adam folder. And you can also maybe make it like experiment 1 underscore Muon versus Adam, like that. Let's create a new file in that new folder. Run Adam learning rate sweep. The main idea here is to find the best learning rate for Adam optimizer for our neural network. So let me just go through all of this. So I'm gonna just say where the different paths for the script and project root are for this folder where we will import stuff, like from run experiments. I'm gonna import run multiple experiments, but we will define this. So I'm gonna print all of the learning rates that we will do experiments with, and these are the names of the experiments. And I'll just go quickly because this is just like running the experiments and then just printing out the result, the summary, and then comparing them, and we can actually get the winner here and printing the winner and then running it all. That's it. So these names will look up, so it will use these names to look up the configs. We define configs for the experiment somewhere else. So inside of this experiment 1 Muon folder, Muon versus Adam, let's make a new file, and it should be experiment configs slash experiment configs.py. So this will create a new folder, experiment configs, as well. And since this file is absolutely huge, I recommend you copy it. And here we have all of the configs. And so look how many different experiments we have, so many. So I'm just gonna copy paste it here. So we have all of the names here. For example, Muon step decay. This is the name, description, optimizer type. We're gonna use this config to select, and then maximum steps, Muon learning rate, Adam learning rate. So we have all of these configs like that. So you can use actually AI to help you figure this out. You need to think like what you want to experiment, etc. Now let's make a new file in the experiment 1 Muon versus Adam folder, and it's gonna be, again, it's gonna be experiment training, experiment trainer.py. And at this point, all of this code should be familiar. So I'm again gonna just copy all of the code because we explained all of this throughout the course. It's all about like learning rate scheduling, setting up parameters, Muon optimizer, setting up Adam optimizer, plotting stuff. So this is just repeated what we already explained. So tell me below if you don't like me just copy pasting it. If you think I should like go through this, then tell me in the comments. And so in both of these new folders, experiment configs, experiment training, I'm gonna add this in it, but it's gonna be empty. Maybe for later use if we need it. You'll see that after you do all of these experiments, you're gonna get a bunch of these files which are just reports and plots of everything, but you don't need to necessarily generate these folders, I should say. Next to run Adam learning rate sweep, I'm gonna create a new file, run Adam optimization suite, and this is still gonna load from the configs and run the configs that we have. So I'm gonna copy paste again because it's basically the same. It's just gonna load stuff from the configs, from this run multiple experiments. These are all of the names of the experiments, of the configs it's gonna run, and then plot, and that's it. Then we will make this run experiments.py. So copy paste this as well because we've explained all this stuff. So it's able to prepare data, run single experiment, run multiple experiments, compare experiments, and all this good stuff. And then main, we have a bunch of arguments defined here. And we also have a new file, run optimal Muon suite. So here we are just running these experiments for the Muon optimizer. and that's it. Everything else is same. Now I will commit everything, save all and commit to GitHub. Then I want to go to extensions in my VS Code type of, and I want to make sure, like, so I have cursor, anti-gravity, VS Code, whatever. If you have some VS Code type of editor, you can install this extension Google Colab. But this does make it kind of difficult to run. So instead, I'm gonna create a new Google Colab notebook, and I'm gonna change runtime type to be GPU, save and connect. Then I'm gonna go and copy, like clone this repository that I just made. So I'm just gonna git clone like that. And then I need to cd, like with this cd into that, into the folder name, but with this percentage sign, and then pip install -r requirements.txt. Let me install requirements. First, we should be able to just run Python train MOE. Let's see if that runs. But this is the base of your like large language model. So now you want to do some research. Now you want to maybe fix some bugs. I do recommend using coding IDE, like Anti-Gravity by Google is actually free right now. So you can fix any bugs if you find, or you can talk to it to help you. Now I'm going to debug this, see if there are any bugs. But because we have the main scaffolding, the main structure, it's going to be easy for you to use code AI editor to fix bugs as well, if there are any. And then this is your base. You can think about research you want to do and do the research from here on. Okay, so it looks like it's actually training. So there is no bugs. And this may be like too many steps. This may take a long time. But it's actually training, so there is no bugs, so everything works. Here in my repository, Blueberry LLM, if you go to this experiment 9 Muon versus Adam, you can get some instructions of how to run these experiments, how to think about them. So, like for example, I can run this command to just run this experiment. But I first need to cd into these proper folders. So if you look at this path, previously it was just noptims and then trying to access this immediately, this file, but that doesn't exist. So I need to cd into experiments and then this folder, or I think I can just add it here as well, like this. So it knows where to look for this. And it looks like the experiments are running and it's training. So there is no bugs. So step 10, step 20, there is no bugs. For writing the paper itself, you will go to overleaf.com and create a new paper. So on this side, you have LaTeX code or LaTeX text, and then it's rendered here. Now you need to know the format, but maybe I recommend you first write your paper in Markdown file, and then you can, get, with the help of AI, convert that to LaTeX. But be careful when writing paper, no AI slop, no AI generated stuff. Like, be very careful that every sentence has its place, that every sentence is meaningful. Actually, Archive stopped accepting reviews in computer science, I believe, because it was like all AI generated by people. So you need to think about your data, analyze it, see what's happening there, understand what's happening there. You can upload images to a folder like this, and then link the images using these like figures, and you specify the path. I think you can ask ChatGPT how to link the image, and I think this is not so difficult. So introduction, you want to just be short and concise. You don't want your paper to be too long. It's better to explain with as little pages and text as possible. And you can do some background and related work if you want, and then explain your methodology. So you can just look at what I wrote here and then edit it, change it based on your experiments. and you can also show the results. Now here I should have colored different colors. So now it's same color, so you can't see. So I can fix this. And I explained here also like the results and the ablations and stuff. I think it's pretty straightforward to write the research paper, although you will spend like a lot of time thinking about related work. But don't get overwhelmed. Don't read too many papers. Don't waste too much time trying to understand like different papers. You need to balance it. All I'm trying to say is this related work could be overwhelming. So make sure you don't like overwhelm yourself. But I think that's it. Writing the paper is quite simple. You've done that in school with presentations, with homeworks. You just analyze, you keep it concise, you explain, you keep it clear, professional. Don't say I did something. You can say the experiment was done, not I did the experiment. Or you can also say we did the experiment. You can say that if you want. But I think there is not much else I can say about writing the paper itself. Just analyzing the results. The most difficult part is like coming up with the idea of the research and executing on it, like knowing which questions you want to answer. So I think that's it for this time. You can find this latex code in the GitHub repository below, so paper.txt and paper PDF as well. Join my school to become AI researcher. We have additional courses here that are not available on YouTube. So from math, PyTorch, neural networks, transformers, large language models from scratch, etc. And the community, you can ask questions and get support. Link below, 7-day free trial, and then just $9 per month. You can check this video that explains more what's contained in here. Thank you for watching and see you in the next video.